On the evening of August 12th, the moon's shadow will race onto northern Spain. For a little under 2 minutes, in cities like Oviedo and Burgos, the sun goes out. The temperature drops, the birds fall silent, and a crown of million-degree fire hangs low. This is the first total eclipse over mainland Spain since 1905. But that shadow now falls on a grid that runs, harder than ever, on the sun. Spain now draws nearly 1 unit in 5 of its electricity straight from sunlight. So when the sun switches off, even for 2 minutes, something must catch that missing power. So here is the question this whole story exists to answer. Are we watching a spectacle or the first test of surviving the loss of our sun? If that question is why you are here, subscribe now and tell me where you're watching. Let's get into it. Part 1. The shadow that arrives at sunset. Let me rebuild this event as a physical thing, rather than a distant headline. On August 12th, the sun itself does absolutely nothing at all. The moon simply slides into the narrow line between the sun and the earth. It is 400 times smaller than the sun burning behind it. Yet it also sits about 400 times closer to where we stand. So the two happen to look almost exactly the same size in our sky. When they line up precisely, the moon casts its shadow onto the surface of the earth. That shadow has a dark inner core that astronomers of the sky call the umbra. Inside the umbra, the sun is completely covered, and that total darkness is totality. On August 12th, that dark core will be roughly 294 kilometers wide, and it will race across the face of the Earth faster than any aircraft you have flown. It begins near the North Pole, far up in the frozen north of Siberia. It crosses the Arctic Ocean and then sweeps over the eastern edge of Greenland. It passes over western Iceland, including the capital city of Reykjavik itself. Then it turns south and finally comes down onto the northern coast of Spain. It clips the far northeastern tip of Portugal on its way past. Finally, it lifts back off the Earth out over the Balearic Islands in the Mediterranean. Stay with me, because one detail about Spain quietly changes this entire story. At the point of greatest eclipse, off Iceland, totality lasts 2 minutes and 18 seconds. Hold that number, because Spain gets a shorter and considerably stranger version of it. Spain sits at the very end of the shadow's long path across the world. By the time the shadow arrives there, the sun is already sinking toward the horizon, so totality in Spain happens not at noon, but in the last hour before sunset. In a Corua, the sun sits only about 12 degrees above the distant horizon. In Burgos, it hangs at roughly 8 degrees during the brief total phase. Out over the Balearic Sea, the corona floats a mere 2.5 degrees up. Let me say that again, because it becomes the hinge of everything to come. The eclipse over Spain happens when the sun is already well on its way down. Its power was fading for the day at the very moment the moon arrives. That single fact is the most reassuring detail in this entire story. But reassuring is not the same thing as harmless, and I will show you why. Because a grid does not truly fear how much power it happens to lose. A grid fears how fast that power vanishes, and how fast it comes roaring back. And an eclipse, unlike a gentle sunset, does not arrive slowly at all. Every one of those darkened cities sits directly on top of a working power grid. Each of those grids is about to lose its sun on a summer evening. And to see why that matters so much, you first need one number. Part 2. The number that rewrote the danger. I want to give you a single figure, and I want you to sit with it. 50 gigawatts, which is 50 billion watts of power at full output. That is how much solar capacity Spain now has installed across its grid. The figure comes from Red Eléctrica de España, the company that actually runs the grid. Their data was updated at the very start of February this year. Let me put 50 gigawatts into human terms that you can actually feel. Spain's total generating capacity from every source combined is about 147 gigawatts. Of that, 50 gigawatts is solar, or roughly 1/3 of the entire national fleet. Solar made up 33.9% of installed capacity by early this year, and last year it generated 18.4% of all the electricity the country used. Hold that, nearly 1 unit of power in 5 came straight from the open sky. Here is the part I really need you to feel down in your gut. This did not happen slowly, over gentle decades of careful and cautious change. In 2025 alone, Spain added about 8.7 gigawatts of new solar. In one region alone, Castilla y León, they added more than 2 gigawatts of it. And that very region sits directly in the belt the eclipse shadow will cross. Now widen the lens from Spain out to the whole of Europe for a moment. The continent's grid operators are all coordinated by a body called ENTSO-E. In the 12 months up to this summer, Europe added 126 gigawatts of capacity. Most of that vast new supply was solar, and it all arrived in a single year. Let me give that number some teeth with one sharp comparison. The last time the moon threatened this grid was back in March of 2015. Back then, the largest solar fleet anywhere on Earth belonged to Germany. That giant fleet stood at about 38.5 gigawatts in total, and Europe just added more than 3 of those, in solar, in 1 year. So the grid the moon meets in 2026 is not a bigger old machine, it is a fundamentally different machine, built at genuinely astonishing speed. And that speed is the whole reason this eclipse is worth 2 hours of your evening. Because solar power carries one strange weakness that no other power source shares. Keep that weakness firmly in mind, because everything ahead of us depends on it. A gas plant has a fuel tank it can draw down whenever it needs to. A nuclear plant has fuel rods, and a hydro dam has a full reservoir behind it. A solar panel has nothing at all but the light striking its face right now. When the light goes, the power goes, instantly, with no coasting whatsoever. So when the shadow crosses Spain, understand exactly what happens electrically. Panel by panel, town by town, the solar output collapses steeply towards zero. Then, a minute or two later, it comes roaring back at nearly full strength, down a cliff and back up a wall, all in the space of a few minutes. And the grid must absorb both moves without a single flicker inside your home. That is the real challenge, and next I will show you how a grid survives it. Part 3. The choir that loses 1/3 of its voices. Let me show you how a power grid actually works, without a single equation anywhere. Picture electricity not as water sitting in a tank, but as a live performance. The grid is a vast choir that has to keep singing every second, forever. On one side stand the singers, which are every power plant feeding the system. On the other side sits the audience, every home and factory demanding sound. The rule of this choir is brutal, and it is completely unforgiving of mistakes. The volume the singers produce must exactly match the volume the audience demands, not roughly, and not on average, but exactly in every single passing second. If the singers grow even slightly too loud, the whole system speeds up together. In Europe, the grid runs at 50 Hz, meaning 50 cycles every second. That number is treated as sacred by the people who guard the grid. Too much power pushes the frequency above 50, and too little drags it below, drift too far in either direction, and protective systems begin shutting things down fast. That is how a small local problem can become a cascade, and then a blackout. So real people, in a real control room, keep this choir balanced live. In Spain, that room is run by Red Electrica, and it is called SECOL. It watches the grid every hour of every day, all year round. They nudge plants up and down, pull from batteries, and import power from France. All of it happens second by second to keep the volume matched to the demand. Now here is exactly what an eclipse does to that carefully balanced choir. On a normal evening, the solar singers grow quiet slowly as the sun sets. The control room has an hour or two to bring other voices in gently. There is no real stress in that at all, because it is simply routine. An eclipse, by contrast, is not a slow and gentle fade at all. An eclipse is a hand clamped over a third of the choir's mouths at once. It happens all together, in the space of barely a single minute. Then, 90 seconds later, the hand lets go and they roar back together. The audience never stops demanding its sound for even a fraction of a moment. So the control room must find replacement voices for a huge share of the choir. It must hold the volume perfectly steady while all those new voices arrive. Then it must push them all straight back out as the solar singers return. Engineers have a single word for this whole difficult ordeal, and it matters. They call it the ramp, and I need you to hold that word tightly. The danger is not the darkness itself, sitting quietly at the bottom of the dip. The danger is the speed of the fall and the violence of the return afterward. Let me put a hard number on that speed, drawn from a recent event. In the 2024 eclipse over California, grid-scale solar fell steeply. It dropped by more than 6,300 megawatts as the shadow crossed. Then it climbed back by more than 6,700 megawatts on the way out. The whole system had to ramp about 10 times faster than a normal day. Picture it plainly now, as a cliff on one side and a wall on the other. The power drops off the cliff, then climbs the wall, while the choir stays in tune. That is exactly what the control rooms are bracing for on August 12th. In Spain, the near-sunset timing makes that cliff lower and the wall shorter. That is real comfort, and I promise I will not simply take it away from you. But Spain has never run this exact test with 50 gigawatts of solar loaded on, and it has never run it just 1 year after something went terribly wrong. To understand that, we first need the 2 eclipses that came before this one. Part 4. What waits inside the 2 minutes of dark? Before the control rooms, let me show you what the crowds will actually see. It is one of the most overwhelming sights available to any human being alive, and the very thing they gather to admire is a clue to a far larger danger. When the moon finishes covering the sun, the sky does not simply turn black. In the final seconds, sunlight streams through valleys and craters on the moon's edge. It breaks into a string of brilliant points that are called Bailey's beads. Then all but one of those beads wink out, quietly, one after another. For an instant, a single blazing point sits on a ring of faint light. That fleeting sight has a name, and people have long called it the diamond ring. Then even the diamond ring vanishes, and what remains behind is the corona. The corona is the sun's outer atmosphere, a crown of pale, silvery light. It streams outward in every direction, far past the black disk of the moon. You cannot see it on a normal day, no matter how hard you might try. The sun's surface is about 1 million times brighter, and it simply drowns it out. Totality is the one and only time human eyes can see the corona directly. It is also the only moment you may safely look at the sun completely unaided. At every other phase you need certified eclipse glasses, or you risk permanent blindness. You cannot feel that damage happening, because the retina has no pain sensors at all. But for those brief seconds of totality, you look up and see a star's atmosphere. Hold that image, because the very next fact about it should not be possible. The visible surface of the sun is about 5,500 degrees Celsius. That is hot enough to vaporize anything we have ever built here on Earth. But the corona, the thin atmosphere floating above that surface is far hotter still. It sits somewhere between 1 million and 3 million degrees. Let me say that again, slowly, because it defies all ordinary sense. The atmosphere is hundreds of times hotter than the surface lying beneath it. Imagine walking away from a campfire and somehow growing hotter with every step you take. That is what the sun does, and physicists have argued about why for a century. They call it the coronal heating problem, and it remains genuinely unsolved today. The leading suspects are tiny magnetic explosions and waves of rippling magnetic energy. But I want to be honest with you in the way this subject truly demands. Nobody has definitively solved that problem even now, after all this time. So when you look at the corona on August 12th, you see an open problem in physics. And that corona is not merely a beautiful crown for people to photograph. It is the source of the solar wind, streaming charged particles toward us constantly. When scientists study it during an eclipse, they study how the sun reaches Earth. Keep that thread in your hand, because I will pull it hard near the very end. The thing people gather to admire is the visible edge of a genuine grid killer. And to understand that properly, we first have to leave the sky for the control room. Part 5. The tools in the room, and the one you cannot buy. I told you the grid is a choir that must stay perfectly balanced live. Now let me show you the actual instruments the conductors hold in their hands. The reassurance in this story is genuinely real, and it lives right here. The first tool is the fastest of them all, and it is the grid-scale battery. Vast warehouses of batteries can respond to trouble in well under a single second. When solar output starts to fall, batteries slam power onto the grid almost instantly. Then, on the recovery, they soak the sudden excess back up again just as fast. They are the reflexes of the modern grid, and they are remarkably new. According to ENTSO-E, Europe's battery capacity fully doubled in just the past year. It reached 29 gigawatts, having doubled inside a single 12-month stretch. Hold that figure, because it changes the odds here more than anything else does. The second tool is pumped hydro, which is water pumped uphill and later released through turbines. It is slower than a battery, but it is far larger in raw capacity. The third tool is the gas peaker plant, a turbine that can spin up fairly quickly. The fourth is the interconnector, the giant cable tying Spain to France and beyond. If one country runs short, its neighbours can feed power to it across those cables. The fifth tool is demand itself, paying big industrial users to briefly power down. That shrinks the audience, so the choir has far less volume left to match. So the conductors are not helpless when the moon reaches out for their sun. They have batteries with reflexes, hydro with muscle, and cables with borrowed strength. On paper, an eclipse near sunset over such a grid is a manageable event. I want to state that plainly, because I do not deal in fear for its own sake. The single most likely outcome on the evening of August 12th is calm. The grid holds, the lights stay on, and only the sky above actually goes dark. But you already sensed a word like this was coming, and here it is. There is one thing on that whole list that solar power quietly erodes over time, and that one thing turns a manageable event into a genuinely nervous one. It is called inertia, and it is the hidden character running through this whole story. Let me explain inertia, because it separates people who understand grids from people who guess. The old plants, whether gas or coal or nuclear or hydro, all spin. They work by whirling a massive metal turbine weighing thousands of tons of steel. And all that spinning steel does something invisible but genuinely vital for the grid. If the grid suddenly loses power somewhere, those spinning masses resist the change. They give up a little of their own motion to hold the frequency steady. That physical stubbornness of heavy spinning metal is exactly what engineers call inertia. It is the grid's shock absorber, its suspension system against any sudden jolt. It buys the human operators a few crucial seconds in which to react. Now hold that idea of a shock absorber, because a solar farm simply has none. A solar farm is a silent field of glass and silicon, and nothing spins. It produces power through pure physics, not through motion, with nothing turning at all. So as a grid trades old spinning plants for solar panels, it loses its shock absorbers. The more solar you add, the twitchier and faster the whole grid becomes. It is lighter and quicker to respond, but it is also quicker to fall over. A heavily solar grid is a light, fast machine taking a corner it never took before, and that is the true reason August 12th is worth watching so very closely. Not because a blackout is likely, because honestly it truly is not, but because a precise scheduled stress lands on a grid stripped of its suspension. And 15 months ago, this exact grid learned firsthand how that feels. But first, the rehearsal the moon ran over Europe 11 years ago. Part 6. The rehearsal the moon ran in 2015. On March 20th, 2015, the moon's shadow crossed the North Atlantic sky. For the first time, Europe's engineers saw an eclipse as a genuine electrical event. It was no longer merely astronomical, but a real and measurable test of the grid. Here is exactly what had changed across the continent by that point in time. Europe, and Germany especially, had finally built enough solar for the moon to matter. For the first time in history, the moon could reach in and pull on the grid. ENTSO-E ran the numbers before the eclipse, and the result truly got their attention. Under clear skies, they calculated the sudden solar drop that would sweep across Europe. They found it could reach as much as 34,000 megawatts of lost power. That is 34 gigawatts, vanishing and then returning within a couple of hours. They described it as roughly 80 medium power plants switching off, then back on. It amounted to a potential 75% swing in Europe's solar output, and ENTSO-E did not hide at all from what their own numbers revealed. They warned, in unusually blunt public language, of a real and serious risk. For the first time, an eclipse could affect the secure operation of the whole system. Konstantin Stachus was the Secretary General of ENTSO-E at that particular time. He called the coming event an unprecedented test for Europe's electricity system. He said control centres across the continent would stay in constant communication throughout. Their shared goal was to cut their reaction times down to an absolute minimum. This was not a statement written to soothe or reassure anyone at all. It was written by people who were taking a genuine risk very seriously. Now watch closely what one single country did, because it reveals how professionals think. Italy's grid operator Terna made a striking and deliberately preemptive choice that day. Rather than let the moon pull its solar down on the moon's own schedule, it acted. Terna preemptively switched off around 5 gigawatts of its own solar in advance. Every plant above a certain size was taken cleanly offline before the eclipse began. Sit with the cold logic of that decision for just a moment longer. They chose to lose the power on their own terms, at a moment they controlled. Better a controlled shutdown, they reasoned, than an uncontrolled slide on the moon's timing. That instinct is one of the very oldest in all of grid engineering. You take the hit on your own schedule, and never on the skies, and you will see that exact same instinct echo again later in this story. So what actually happened across the whole of Europe on that March morning? The grid held completely, from Portugal in the west all the way to Poland. The lights stayed on everywhere, and the careful coordination worked exactly as planned. The batteries, the hydro, the gas, and the cross-border cables all did their jobs. Afterward, Stachus called the day a clear success of European cooperation. It was, by absolutely any measure, a genuine triumph of careful preparation. But hold two things about 2015, because they both matter enormously now. First, The whole system then rested on a solar fleet far smaller than today's. The giant, remember, was Germany alone, at 38.5 gigawatts. Spain by itself now runs a full 50 gigawatts of solar on its grid. Second, the 2015 grid was still heavy with old spinning plants everywhere. It was full of inertia, full of shock absorbers, and sturdy by today's standards. So beware the comforting line you will surely hear about all of this. Someone will say the grid handled 2015, so 2026 is nothing. That framing misses what has actually changed so completely that it genuinely misleads. It is like saying a bridge held a heavy load easily a decade ago. Then quietly you removed half its support beams and tripled the traffic across it. The 2015 grid and the 2026 grid are simply not the same bridge. And to see the new, lighter bridge under real stress, we must cross an ocean. Part 7. 2 grids, 1 moon, 2 different answers. On April 8, 2024, the moon's shadow crossed all of North America. It passed over 2 very different power grids that were both watching it closely, and those 2 grids answered the exact same eclipse in 2 completely different ways. The difference between their answers is the most useful thing to grasp before August 12th. So let me walk you through both of them, carefully and slowly. Start with Texas, a grid that is heavy with both solar and natural gas. When the eclipse rolled across the state, the numbers turned dramatic very fast. According to the United States Energy Information Administration, Texas lost roughly 9 gigawatts of solar. One independent analysis put the collapse even more starkly than that. Texas solar output fell from about 13.8 gigawatts near the middle of the day. Just 45 minutes later, it sat at only about 800 megawatts. That is a 94% collapse in a mere 45 minutes flat. Then, it climbed almost all the way back up again within the following hour, down a cliff and straight back up a wall, exactly as I described earlier. So what caught Texas when almost 9 gigawatts of sunlight suddenly vanished from it? Natural gas, overwhelmingly, roaring up to fill the enormous hole in supply. The government's analysis found gas replaced about 80% of all the lost solar. Gas plants added more than 6 gigawatts of output in a single hour alone. Coal and batteries each chipped in less than a gigawatt between the two. Texas answered the eclipse by burning fuel and reaching straight for its tanks. It worked exactly as intended, and the Texas lights all stayed on. Now cross the whole continent over to California, under that very same moon. California had spent years building something that Texas simply had not built. It had built an enormous fleet of grid-scale batteries across the state, and when the shadow crossed California, those batteries quietly did all the work. They had drunk in power all morning long while the sun blazed overhead. The instant the sun faltered, they turned around and poured it all back out. Analysts watched California storage flip from charging to discharging within a single hour. It swung from soaking up power to delivering nearly 3 gigawatts to the grid. And in California, natural gas barely registered any change at all that day. The batteries almost entirely backfilled the solar slump completely on their own. So look at those 2 very different answers side by side for a moment. 2 grids, 1 moon, and 2 utterly different responses to the same event. Texas answered the shadow with fire, and California answered it with stored power. And that is precisely the question now hanging over Europe on August 12th. Which of those 2 grids does Europe most closely resemble in this moment? For most of the last decade, the honest answer would have been Texas. Europe would have leaned hard on gas to fill the sudden gap. But remember the one number I asked you to hold on to earlier? Europe's battery fleet doubled to 29 gigawatts in a single year. Europe is transforming from a Texas grid into a California grid right now, and August 12th lands squarely in the middle of that ongoing transformation. It is the first continent scale test of whether batteries can replace the fire. Now here is the turn that matters most in this entire story. When people imagine the risk of an eclipse, they picture only the darkness. They picture the trough, that quiet moment of the very least power. But engineers will tell you the trough is almost the easy part of it. You can see the trough coming decades in advance of the day itself. You know its exact depth, and you know its exact timing to the second. The real danger is the walls standing on either side of that trough. It is the speed of the fall and the violence of the return afterward. In 2024, the recovery ramp ran about 10 times faster than usual. The darkness is the thing that everyone stands there and looks at in wonder. The ramp is the thing that can actually hurt the machine underneath it all. And almost nobody in the crowd will even know that it happened at all. That pattern, the visible event hiding the real danger, returns again and again. Next, it returns on Spanish soil on an otherwise ordinary spring afternoon. Part 8. The afternoon a whole peninsula went dark. Now I must show you why this eclipse, over this country, carries a real edge. To do that, I have to take you to April 28th, 2025. It was a warm spring afternoon across Spain and Portugal, just over a year ago. Let me rebuild what happened not as a news event, but as a physical process, because the seconds in this particular story are very nearly the whole story. At 33 minutes past 12, in the middle of the day, the grid failed. The Iberian Peninsula's grid shed about 15 gigawatts of generation all at once. Let me tell you exactly how fast that enormous loss actually happened. In about 5 seconds, and no longer than that at all. 15 gigawatts, roughly 60% of everything the grid was then supplying, gone, it vanished in the time it takes you to read this single sentence aloud. The grid then did what any grid does under such a sudden, savage blow. It came apart, quickly and violently, right across the peninsula. The frequency, meant to sit rock steady at 50 Hz, began to collapse fast. It sagged down toward 47 Hz as the whole system lost its footing. The voltage, meant to hold near 400,000 volts, surged upward instead. It spiked toward 435,000 volts on the high-tension lines. The cables to France and to Morocco tripped and disconnected in the chaos. That isolated the peninsula completely from the neighbours who might have helped it. Within moments, most of Spain and most of Portugal fell into total darkness. Not a single city, and not one region, but an entire peninsula at once. Tens of millions of people lost their power in the very same instant. Trains stopped dead between stations, and traffic lights died in place everywhere. Hospitals fell back onto their emergency generators simply to keep going. Phone networks buckled and failed under the sudden overwhelming load. For most of the peninsula, the power stayed off for around 10 long hours. Full restoration took the better part of 16 hours after that. Only 2 places kept their lights burning steadily through the whole ordeal. The Balearic Islands and the Canary Islands both stayed fully lit. And the reason those islands survived matters a great deal for the eclipse ahead. Those islands run on their own separate grids, not tied to the mainland collapse. Isolation, in that particular moment, turned out to be their salvation. The peninsula, all wired together as one, fell together as one. Now I must be extremely careful with exactly what comes next in this story. This event was weaponized within hours by people carrying their own agendas. A clean, satisfying and convenient story spread across the internet very fast. Spain went dark, they said, because it relied far too much on renewables, too much solar, too much wind, and not nearly enough spinning steel. It was politically convenient, and it was simple, and it was also wrong. Hold that word wrong, because the actual evidence is quite clear on it. The investigation into the blackout was genuinely enormous and deeply detailed. ENTSO-E convened an expert panel made up of dozens of specialists. They produced a technical report running to many hundreds of pages. The Spanish government and Red Electrica each ran their own investigations too, and their shared conclusion was not simply too much renewable energy. And that is exactly where the next part of this story begins. Part 9. The story about the blackout that was not true. Let me tell you what the investigators of the blackout actually found instead. The collapse was multifactorial, meaning it came from a whole chain of separate failures. It came from failures in how voltage and reactive power were being controlled that day. It came from oscillations moving strangely through the connected system. And it came from generators disconnecting in a rapid, cascading sequence. The villain, crucially, was not solar power somehow flooding the grid. Here is the part that got buried completely under all the political noise. Investigators pointed to renewables and batteries not as the cause of the collapse. They pointed to them, properly deployed, as part of the eventual solution. Sara Argason is the Spanish energy minister who addressed those official findings. She noted something quite pointed about how the plants disconnected that afternoon. Some generator disconnections happened before the voltage even crossed the regulated thresholds. In plain language, some plants tripped off exactly when they should not have. That early tripping turned an already serious problem into a genuine catastrophe. So the honest lesson of April is not that renewables somehow cause blackouts. That is the misinformation version, an omission dressed up as an insight. The honest lesson is subtler, and in a strange way it is more unsettling. A modern grid running light on inertia is a faster, more delicate machine overall. Remember the shock absorbers, the spinning steel I carefully described to you earlier? A grid with fewer of them can lose its balance with frightening speed. When something goes wrong, it can go wrong almost completely, in seconds. Older, heavier grids simply could not fail that fast, or that totally. The blackout was not caused by the sun, and not by solar panels either. But it was a vivid, national 10-hour demonstration of something important. It showed just how quickly this new kind of grid can lose its footing. 5 seconds, 60% of supply, and a whole peninsula in the dark. That happened on this exact grid only 15 months ago. Let me say that again, so that it lands with its full weight on you. The very grid the Eclipse now crosses fell over completely last spring. It fell not from an eclipse, but from a fault that nobody saw coming. And that is precisely why the Ghost of April matters so much right now, because it proved something specific and lasting about this exact machine. It proved the grid is now light enough, and fast enough, to be fragile. Light enough that a disturbance and a hidden weakness can align dangerously. And when they do align, the margin for error is measured in seconds. Keep that thin margin in mind, because an eclipse is itself a disturbance. It is a large, scheduled disturbance arriving on a newly nervous grid. Now, I want to be completely fair, and I refuse to overstate this. The eclipse and the blackout are simply not the same kind of threat. The blackout was a sudden, unforeseen fault deep inside the machine. The eclipse is the exact and total opposite of unforeseen. It is quite possibly the most predictable event in all of science. We know its path to the meter and its timing right to the second. There is a table, computed decades ago, for when the shadow reaches Burgos. Nothing at all about the eclipse itself will come as a surprise, and that predictability is the operator's single greatest weapon on the day. But a weapon only helps if the hand that holds it stays steady. Whether that hand stays steady is the whole question of the next part. Part 10. The Ghost Standing in the Control Room. Put yourself now in a control room chair inside Seacole for a moment. It is early August 2026, and a shadow is steadily coming. On your screens, a scheduled event approaches that you simply cannot cancel. You cannot delay it, and you cannot fully predict its effect on the grid. On August 12th, the moon will pull down part of your 50 gigawatts of solar, and you must manage that on the very same grid that fell last spring. I want to be precise here, because false precision would help no one at all. Every structural advantage genuinely points toward the grid holding on the 12th. The operators will pre-position their batteries well in advance of the shadow. They will schedule hydro and line up power imports coming from France. They can even do exactly what Italy did back in 2015. They can take some solar offline early on their own controlled terms. They hold the 2015 playbook firmly in their experienced hands. They have the 2024 data from both Texas and California. They have a battery fleet that doubled in size in a single year, and they have the near sunset timing working quietly in their favour. Every one of those factors points toward a genuinely calm evening ahead. Hold on to that thought, because I truly do mean it sincerely. The most likely outcome, by a very wide margin, is an uneventful grid, a forgettable evening for the machine, and an unforgettable one for the sky. Even the Spanish utilities are saying almost exactly that same thing publicly. Endesa, a major power company, published a calm explainer about the whole event. They said the eclipse will have only a limited effect on the system. It happens, they note, when photovoltaic production is already in its descending phase. They describe Red Eltrica as the control tower, watching everything around the clock. The power will flow, they promise, whether there is an eclipse or not. And here is the honest truth of it. They are very probably right. So why does the ghost of April still stand in that quiet control room? Because April proved something that no amount of careful planning can fully erase. It proved this specific grid is now light enough to fall over fast. The eclipse is not likely to be the disturbance that finally topples it, but it is a real, large, scheduled disturbance landing on it nonetheless. It arrives on a grid recently shown to have alarmingly thin margins. It arrives in the middle of a transformation that keeps stripping out inertia. And here is the thing the corona watchers out in the fields will never see. They will look up at a black sun ringed with fire and simply gasp. And in a windowless room, engineers will watch a completely different sky. It is a wall of screens showing frequency and voltage and power flow. Two audiences, one single event, unfolding at the very same moment. One group watches the most beautiful thing in the entire sky above, the other watches the most fragile thing on the ground below them. And we will not know whose view mattered more until it is finally over. Now, I promised you the deeper structure this whole story is built upon. There are two independent timelines converging on the same place at once. The eclipse is timeline 1, the shadow crossing the vast solar fleet, but almost no one has connected the second timeline to the first. On the very same night, a second event arrives over that darkened sky, and to reach it, we first need the machine that pretends to spin. Part 11. The machine that learned to pretend it spins. I told you a solar grid quietly loses its precious inertia over time. It sheds the spinning steel that used to be its reliable shock absorber. Both of those things I told you are completely and literally true. But I left out the frontier, and the frontier is where the real drama lives. Because engineers have been quietly building a clever way to simply fake it. They can now make batteries and silicon behave much like a spinning turbine. Whether that trick works, at full scale, under real stress, is the century's question. Let me explain the trick itself, because it is genuinely quite elegant. Most solar and battery equipment installed today uses a grid-following inverter. The name of it honestly tells you almost everything you need to know. A grid-following inverter is, at its very heart, only a follower. It listens carefully to the grid and finds the existing rhythm there. That rhythm is the 50 Hz beat set by all the big spinning machines. Then it simply plays along, feeding its power in perfect time with that beat. It is a backing musician, matching a beat that is already there. It cannot set the tempo of the song, and it can only follow. And here is the catch buried inside that fact that should worry you. If the machines setting the beat go away, the follower has nothing to follow. Take away the drummer entirely, and the whole backing band falls silent. None of them ever actually learned how to keep time all alone. That, in one sentence, is the hidden fragility of a solar-heavy grid. You end up with many musicians, none of whom can hold the beat themselves. All of them wait on a drummer who grows quieter with every passing year. When a disturbance strikes, a grid like that can lose its rhythm terrifyingly fast. This was part of what made the April blackout in Spain so severe. The grid was running light on the machines that could actually set the beat. Keep that drummer in your mind, because now the story turns genuinely hopeful. The newer technology is called, fittingly, a grid-forming inverter instead. And a grid-forming inverter is not a passive follower at all. It is a leader, and that single fact changes absolutely everything. Through fast, clever software, it does not just match an existing beat, it generates one, creating a stable rhythm out of essentially nothing. It does what a spinning generator does, but entirely without the spinning. It can even mimic real inertia in the instant a disturbance strikes. It throws power onto the grid in the very first fraction of a second. It resists the change exactly the way heavy spinning steel would resist it. It is in effect a battery that has learnt how to pretend it spins. A machine with no moving parts, behaving as if it had thousands of them. Engineers call the quality it provides synthetic inertia, or virtual inertia. And it is very nearly the holy grail of the entire clean energy transition. If grid-forming inverters spread widely enough, the whole inertia problem starts to dissolve. You could run a grid on almost pure solar and batteries alone, and it could still hold its rhythm and absorb its shocks perfectly well. The batteries themselves would quietly do the job the old turbines once did. That is the future the optimists are actively building toward right now. And it is a genuinely realistic future, and not some distant fantasy. The technology already exists, and it is already being installed today. Some of the world's most solar-heavy grids already lean on it heavily, but the small word if is doing enormous work inside that hope. Synthetic inertia is newer, and it is far less tested at massive scale. It depends on software behaving perfectly in the single worst possible moment. A turbine resists change purely because of the unbreakable laws of motion. Those laws never crash, and they never carry a hidden software bug. A grid-forming inverter resists change because of code and control systems instead. And code is only ever exactly as good as the engineering behind it. An eclipse is precisely the kind of large, clean, scheduled event to test it. It is where you finally learn how the new technology behaves under real stress. So when the shadow crosses Spain and the batteries hold the frequency, watch closely. Part of what is being tested there is completely invisible to everyone outside. It is whether the machine that pretends to spin can truly do the job. That is not a small question tucked quietly away in an engineering paper. It is the whole bet of the century, being placed for 2 brief minutes. It is placed over a darkened country, in full view of the watching world, and almost no one gazing up at the sky will know the bet even exists. But before we reach the sky, one more thing about the grid itself, because this eclipse is far from the only time that the sun disappears. A smaller version of the very same thing happens every single day. Part 12. the daily eclipse no one ever notices. Here is a simple truth that reframes this entire event for you. From the grid's point of view, an eclipse is just a sudden loss of the sun. The sun it depends on gets taken away fast and then given back. And a version of exactly that happens every single evening, everywhere. It is called sunset, and it is completely relentless in its arrival. Every evening, on every solar-heavy grid on Earth, the sun goes down. All that solar power fades away towards zero as the light finally dies, and it fades at the single worst possible moment of the whole day. It fades right as people come home from work in the evening. They switch on their lights and begin to cook their dinners. They charge their cars, and they drive the demand steeply upward. Grid engineers even have a name for the shape this makes. On their charts they call it the duck curve, for its distinctive outline. Solar floods the grid all through the middle of the sunny day. Then it falls away sharply in the evening, exactly as demand spikes hard. The operators must then conjure a huge surge of replacement power. They must do it in the narrow space of just a couple of hours. It is, in genuine slow motion, an eclipse that happens every night. The eclipse of August 12th is simply that same challenge, compressed hard. It is the sunset ramp squeezed from 2 hours down into 2 minutes, and it is dropped into the middle of the day entirely unexpected. That is exactly the reason it makes such a genuinely useful test. It stresses, in one controlled burst, the capability a solar world truly needs. That capability is the plain ability to lose the sun suddenly and survive. Hold that idea firmly, because it has a very familiar name already. That capability is storage, batteries, pumped hydro, anything that saves the surplus day. It lets you take power when the sun is generous and pouring it out. And it lets you give that power back when the sun is entirely gone. The whole future of a sun-powered grid comes down to that one thing. It comes down to storing enough of the day to survive the coming night, and to survive the sudden nights, the clouds and the eclipses as well. Europe doubling its batteries to 29 gigawatts is not just eclipse preparation, it is the story of a whole civilization building shock absorbers in a hurry. It is racing to build them before its own vulnerabilities finally catch up. So when the shadow crosses Spain and the batteries hold the line, understand it. You are watching a preview of how every grid on Earth must work. Every grid, all the time, for the entire rest of this century. A world running on the sun must learn to survive losing the sun. It must survive it over and over, on many completely different schedules. On the moon's schedule, on the weather's schedule, and on the sun's own. August 12th is a rehearsal for a play that never once closes, and there is a harder edge to all of this that I will not hide. The more successful the solar transition is, the more exposed the grid becomes. Every gigawatt of solar is another gigawatt the moon can pull down. It is another gigawatt a passing cloud bank can erase in minutes. It is more spinning steel retired, and more precious inertia surrendered. This is not an argument against solar power in any way at all. Solar power is cheap, it is clean, and on most days it is extraordinary. It is only an argument for understanding the deep bargain underneath it. The sunnier your grid becomes, the more it needs a real nervous system. It needs batteries and controls and a genuine kind of institutional humility. It needs them fast enough to survive the days when the sun is missing. The eclipse is the one moment that whole bargain becomes visible for 2 minutes. The rest of the time, that bargain stays almost completely invisible to us, and that is exactly why almost no one ever stops to think about it. Until a peninsula suddenly goes dark on an otherwise ordinary afternoon. Now, at last, we can leave the grid behind and simply look up. because the same night that shadow falls, a second sky quietly arrives. Part 13. The second sky that falls the same night. Here is the convergence, and it is stranger than it first appears to be. Very few people have ever put the two halves of this night together. Once you actually see it though, you honestly cannot unsee it again. The eclipse happens because the moon passes directly between Earth and the sun. There is only one single phase of the moon when that can happen. It is the new moon, when the moon sits over on the sun's side. Its lit face is turned away from us, and it is invisible in our sky. An eclipse is simply a new moon that happens to line up perfectly. So on the night of August 12th, after the sun finally sets, notice something. There is no moon at all left anywhere in the whole night sky. The sky goes as dark as a northern summer sky can possibly go, and that deep darkness matters far more than you might first guess. Because that very same night is also the sharp peak of the Perseids. The Perseids are the most beloved meteor shower of the entire northern year. Every August, the Earth ploughs straight through a long river of comet debris. Specks of ancient dust slam into our upper atmosphere at tremendous speed. They strike at 59 kilometers per second, the fastest of any major shower. They burn up in bright streaks of light we simply call shooting stars. At its peak, under ideal skies, the Perseids can produce 100 an hour, and the predicted maximum this year falls right on the 12th into the 13th. Now here is exactly why the year 2026 is so genuinely special. Most years the Perseid peak is badly spoiled by bright, washing moonlight. A bright moon washes out all but the very brightest meteors overhead, but this year the peak lands precisely on the night of the new moon. It is the very same new moon that also produces the eclipse itself. So the sky on that night is as dark as it will ever get, and the meteors will be about as visible as they ever are. Astronomers are calling it the best Perseid condition since 2021. Nothing at all comparable is expected again until the very end of this decade. Follow the timeline of that single remarkable day in northern Spain with me. In the early evening, the moon slides in front of the sinking sun. For 90 seconds, day becomes night, and the corona blazes overhead. The sun then sets, and the twilight slowly fades away into blackness. And then, into that moonless dark, the Perseids finally begin to fall. Debris from a comet streaks silently across the very same darkened sky. Hours earlier, that exact patch of sky had held a total solar eclipse. Two celestial events, from two entirely unrelated mechanisms, share one single night. One comes from the geometry of the moon and the sun aligning. The other comes from the ancient orbit of a distant icy comet. They arrive over the same darkened patch of Earth within a few hours. Picture yourself standing in an open field near Len on that evening. You could watch a total eclipse of the sun at sunset itself. Then you could watch a full meteor shower at midnight without moving your feet. Hold that picture, because the source of those meteors deepens the strangeness. And that source is a mountain of ice you really ought to meet next. Part 14. The mountain of ice that feeds the shooting stars. Let me tell you where those falling meteors actually come from originally. The Perseids are shed each year by a comet named Swift-Tuttle, and Swift-Tuttle is not some small harmless pebble drifting through space. Its nucleus is estimated at around 26 kilometers across in size. That is a mountain of ice and rock far wider than most cities are. It swings through the inner solar system on a very long orbit. That orbit takes roughly 133 years to complete just once. It last rounded the sun in 1992 within living memory. It will not return again until around the distant year 2125. Yet every August, whether the comet is near or far, we cross its trail. We pass through the dust it has shed over many thousands of years, and that dust, burning up in our air, gives us the whole shower. So the meteors you would watch on eclipse night have a strange origin. They are pieces of a 26-kilometre comet burning in our atmosphere, and they fall above a country bracing itself to lose its own sun. Hold that scale for a moment, because it is genuinely worth respecting. 26 kilometres is more than twice the width of another famous object. The object that ended the age of the dinosaurs was smaller than this. That impactor at Chicxulub was roughly 10 to 15 kilometres across. Swift-Tuttle is a larger body than the very one that killed them. Now I want to be careful and completely honest with you here. Swift-Tuttle is not a threat to us on any near horizon at all. Its orbit is well studied, and its next passes are carefully calculated. It poses no impact danger in our lifetimes, or in our children's, but its sheer size has still earned it a certain grim fame. Some astronomers have called it one of the most dangerous known objects. They mean over the very long run, across many thousands of years ahead. A comet that large crossing Earth's path genuinely commands real attention. Its orbit is nudged over time by the powerful gravity of Jupiter, and over long enough spans, such orbits are hard to predict perfectly. So the honest framing here is neither panic nor easy dismissal. The shower itself is completely harmless, a gift of light every single August. The parent body is harmless now, but it is genuinely enormous in size, and it will keep crossing our neighbourhood for many ages to come. Keep that sharp contrast in mind, because it is the pattern once again. The beautiful thing overhead is debris from something far more serious below. The shooting stars are only crumbs from a mountain that crosses our road. There is a quiet poetry to the whole arrangement of that night. A grid loses its sun to the moon in the early evening hours. Then the sky fills with sparks from an ancient comet by midnight. Two objects from the depths of space touch one country in one night. One steals the sun for 2 minutes, gently and right on schedule. The other rains down harmless fire from a distant mountain of ice, and a very human machine sits between them, quietly holding its breath. Now let me pull back from the comet and the grid alike for a moment. Let me follow the shadow itself on its long journey across the world, because the path this eclipse takes is stranger than the single word Spain suggests, and it explains why some serious eclipse chasers are skipping Spain entirely. Part 15. The shadow's long walk from the pole. The shadow begins its journey at the very top of the world. That dark core, 294 kilometres wide, first touches Siberia. It touches down in the far north, almost at the North Pole itself. And right at the start, it does something genuinely unusual. It sweeps from east to west across the frozen top of the globe. That is the opposite of how we usually imagine shadows moving at all. It is a quirk of geometry when the path runs so near the pole. It crosses the frozen Arctic Ocean, over endless ice and empty water. It passes over the eastern edge of Greenland shortly after that. It crosses ice sheets kilometres thick where almost no one at all lives. Then it comes down over the North Atlantic and heads toward Iceland. And Iceland, it turns out, is the connoisseur's choice, for a clear reason. When the shadow reaches Iceland, the sun is still comfortably high overhead. It sits around 24 degrees above the horizon in Reykjavik itself. That higher sun means a cleaner, less obstructed view of the corona. And it means you are not gambling everything on a clear horizon. Out on the Snæfellsnes Peninsula, in towns like Lafsvåg, totality runs longer. It stretches past 2 full minutes, longer than anywhere on the Spanish mainland. The trade-off is Iceland's famously fickle and constantly shifting weather. A country that changes its skies every hour is its own kind of gamble. But for the chasers who measure their lives in eclipses, Iceland genuinely calls. It offers the highest sun and the longest darkness anywhere on this path. Many of them are quietly going there instead of going to Spain. They are willing to bet everything on a single break in the clouds. Then the shadow leaves Iceland behind and races onward towards Spain. And as it goes, it is also steadily racing the sun towards sunset. This is the geometry I keep returning to, now seen as a chase. The shadow moves south and east across the great curve of the Earth, and the sun, from the ground below, sinks lower with every passing minute. By the time the shadow reaches Spain, the sun has dropped very low. It has fallen to those horizon angles, 12 degrees, 8 degrees, then 2. The shadow arrives in Spain almost completely out of daylight. It catches the sun in the very last act before it finally sets. That is not a coincidence that anyone could ever have arranged. It is simply where this particular ribbon happens to fall on the map. And I want you to appreciate the sheer speed of the thing itself. The shadow crosses the Earth at many thousands of kilometers per hour. In some places it moves faster than the very speed of sound. Picture yourself standing in an open field near Len as it comes. In the final moments before totality, you would turn and look west. You would see a wall of darkness rushing toward you across the land. It is the shadow of the moon, moving faster than sound itself. And it would swallow you whole, right where you happen to stand. For 1 minute and 45 seconds, you stand inside another world's shadow. Then it tears on past you to the east, and it is gone. That is not a metaphor at all, but the literal physical event. A piece of the moon's shadow, hundreds of kilometers wide, sweeps past. It moves faster than a rifle bullet straight across northern Spain. It reaches the Mediterranean and lifts back off the Earth entirely. The whole traverse of the planet takes only a few short hours. Blink on the scale of a single day, and the whole thing is done. And in those few hours, it hands science something it truly cannot buy. The 2 minutes science still cannot buy. Here is a question about the eclipse that genuinely surprises most people. Why does a total eclipse still matter to modern science at all? We have space telescopes and probes flying right through the sun's atmosphere. We have satellites staring straight at the sun every second of every day. So why do researchers still chase the shadow all across the world? The answer reveals the real limits of even our very best machines, and it ties straight back to the larger danger I hinted at before. Here is the core of it, put as plainly as I can. To study the corona from space, scientists use an instrument called a coronagraph. A coronagraph places a small disc right inside the telescope itself. That disc blocks out the blinding face of the sun for the camera. It creates a kind of artificial eclipse, on demand, running continuously. It is an ingenious tool, and it honestly never once stops working. But it carries one deep and fundamental limitation with it. Light bends and scatters around that small blocking disc inside the telescope. So a coronagraph cannot cleanly see the region right next to the sun. It cannot see the inner corona, the very lowest and densest layer. And that inner layer happens to be the most important one of all. It is where the corona's deepest mysteries are actually born. It is where the solar wind first begins its long journey toward Earth. The artificial disk always blocks just a little too much of it. There is a ring of prime real estate we simply cannot image well. And that is exactly the region a total eclipse suddenly reveals. When the moon blocks the sun, it does so almost perfectly, cleanly. It blocks right down to the very edge of the visible surface. And it does so without the scattered light of an artificial disk. For those minutes of totality, the inner corona snaps sharply into view. It appears with a clarity no orbiting coronagraph can ever match. The moon is simply a better occulting disk than anything we have built. So during an eclipse, scientists measure that hidden layer directly and clearly. They measure its temperature, its structure, and its magnetic shape. They study the exact place where the coronal heating problem truly lives. They study where the solar wind is born and where it accelerates outward. This is not ceremony at all, and it is certainly not nostalgia. It is genuine data we cannot gather in any other way at all. It is available only in the ribbon and only during totality itself, and it lasts only a couple of fleeting minutes at a single time. Remember exactly why that hidden layer matters so very much to us. The inner corona is precisely where all our space weather is born. It is where the sun decides how much material to fling at us, and it decides how fast to fling that material toward our planet. The region hardest for us to see is the region we most need. We need it to forecast the solar storms that threaten our power grids. So the 2 minutes of an eclipse are not merely beautiful to watch, they are a rare, clear look at the birthplace of a real threat. The corona the crowds photograph for wonder is something else entirely to scientists. To them, it is a diagnostic image of a genuine danger overhead. The same light, seen in two completely and utterly different ways. I will add one honest note here, because inflation helps absolutely no one. There is often talk of grand citizen science campaigns during big eclipses. Thousands of amateurs are networked along the path, building a continuous record. Some of those efforts have been genuinely real and valuable before now. I cannot name the specific programs for this one with real confidence, so I will simply not pretend to you that I actually can. But the underlying truth still stands very firmly on its own. A total eclipse turns the whole path into a single instrument. It becomes a scientific instrument several thousand kilometers long, but briefly, and the people standing inside it are inside a rare natural experiment. It is one that our most advanced technology still cannot fully replace. Now let us turn, at last, to those people out there themselves. Part 17. What the darkness does to your body. I have given you physics and engineering in genuinely heavy doses now. I do not want you to walk away thinking an eclipse is only data. It is not merely data, but a physical experience that completely overwhelms you. It is one of the most powerful things a living person can ever feel, and I want to describe what the crowds out there will actually feel. It does not begin with the darkness at all, strangely enough. It begins of all things with a growing sense of pure wrongness. In the last 20 minutes the moon eats away more of the sun. The light does not merely dim as the crescent thins away, instead it slowly and unmistakably begins to go entirely wrong. Shadows sharpen unnaturally because the sun is shrinking down toward a point. The world takes on a strange, silvery, faintly metallic sort of quality. It looks like an overexposed photograph you have somehow never seen before. It is a light you cannot quite name in any season of your life. The temperature starts to fall, quite noticeably, right on your skin. It drops several degrees in the space of just a few minutes. A breeze often picks up too, a real and genuinely sudden wind. Eclipse watchers even have a name for it, the eclipse wind. It stirs to life as the sudden cooling changes the air around you, and the animals themselves begin to react to the false dusk. Birds go quiet and start heading in early toward their roosts. Crickets can begin to sing, fooled into thinking it is truly night. Cows have been seen calmly walking back toward their barns. The whole living world begins, quietly and together, to make a mistake. Then, in the final minute, it accelerates past anything gradual at all. Look down at the ground and you may just see shadow bands. They are faint, rippling ribbons of light and dark, moving fast. They race across pale surfaces like sunlight on the floor of a pool. They come from the last thin sliver of sunlight through turbulent air. They are notoriously hard to photograph and genuinely eerie to witness live, and with the sun low in Spain, that rippling effect can be striking. Then, if you look west, you may actually see the shadow itself, The moon's shadow rushes toward you across the land, faster than sound, and then it arrives, and the very last bead of sunlight vanishes. The diamond ring flares and dies away in a single instant. Totality falls upon you like a heavy lid closing shut overhead. The change is not gradual in any way, arriving instead as a sudden switch. One moment there is that silvery, uneasy, wrong-feeling twilight around you. The next, the sun is a black hole in the sky ringed with fire. You stand in the middle of the day, somehow deep inside night. Stars come out overhead, sudden and real and completely unexpected. Planets appear too, Venus first, and quite likely others beside it. And here is the single detail that truly undoes people out there. All the way around you, 360 full degrees, the horizon glows. It glows with the warm colours of sunset in every single direction. Orange and pink and red, the whole way around the sky, because you are standing in a pool of shadow only kilometres wide. Beyond its edge, in every direction, the sun is still shining normally. You are inside the shadow itself, looking out at distant daylight. In Spain, the low sun tints that whole corona a warm, reddish gold. It is a black sun in a burning twilight near the horizon line. It will be a version of totality most chasers have never once seen. There is a reason grown adults openly weep during those 2 minutes. There is a reason people reshape their entire lives around chasing it. It does not look like a photograph, and it does not look like a video. It bypasses the part of your brain that quietly processes ordinary images. It goes straight to something far older and deeper inside of you. And then, all too soon, the diamond ring flares on the far side. The light floods back, the warmth returns, and the birds stir again. 2 minutes to undo a lifetime of assuming you knew the sky. That is what is truly at stake for the people in the path. Not data and not gigawatts, but exactly that overwhelming thing. And the one force that can steal it away is not the moon. It is the weather, waiting patiently down at the horizon. Part 18. The Gamble at the Edge of the World. I have spent much of this story inside control rooms and orbital mechanics, but another whole layer decides whether anyone sees the eclipse at all. It has nothing to do with gigawatts, and nothing to do with geometry. It has everything to do, instead, with the fickle clouds overhead. Here is the cruel geometry of the Spanish eclipse laid out plainly. It happens near sunset, with the sun sitting very low in the sky. It sits as low as 8 degrees above the horizon in Burgos. It sits at only about 12 degrees up in coastal Ecorua. It sits at 2.5 degrees over the distant Balearic Sea. That very low sun is a genuinely double-edged thing for the watchers. On one edge, it is spectacular in a way that is hard to describe. It gives a black sun ringed with red fire near the landscape. Most chasers never once get that, because most eclipses ride high overhead. But on the other edge, it is a real and serious gamble. When the sun is that low, you look through a great deal of air. You look through the haziest, most cloud-prone slice of the whole sky. That is the part right down at the very edge of the horizon. A single bank of cloud on the western skyline can erase everything. If the sun were riding high, that same cloud would not matter. But at 8 degrees up, it can hide the entire eclipse from you. You need not just clear skies, but a genuinely clear horizon too. And you need it in the exact direction the sun is setting that evening. This is why choosing where to stand becomes its own careful science. Chasers pore over decades of cloud statistics for each town along the path. Some bet on the drier interior around Zaragoza and the Ebro Valley there. In that region, the August skies tend to run the clearest of all. Douglas Duncan is an astronomer from the University of Colorado. He chose Zaragoza precisely for its favourable clear sky odds this August, and he put his finger squarely on the deeper truth of all this. The biggest wrong idea about eclipses, he says, is a simple one. People think that seeing a 90% eclipse is most of the show. It is not most of the show, but honestly almost none of it. A 99% partial eclipse is still just ordinary daylight. The corona stays completely invisible and the stars do not appear. It is the difference between the cliff edge and actually stepping off. Totality is not the top of a scale of brightness at all. It is a completely different phenomenon, inside a very narrow ribbon. Only those standing inside the ribbon, a couple 100 kilometers wide, see it. Jay Anderson runs a respected eclipse weather site called Eclipsophile. He notes just how low the corona will hang over the Balearics that night. It will float only 2.5 degrees above the open sea. That is a razor-thin margin against any bank of horizon cloud, and that narrow ribbon is about to receive an enormous human tide. Totality is crossing a populated, accessible, beautiful country in mid-August. That falls squarely in the very peak of the European holiday season. The result is one of the largest voluntary migrations there is anywhere. Hotels along the centerline have been fully booked for many months already. Small towns that see a handful of visitors expect tens of thousands, and that human surge is a genuine kind of stress test all on its own. It strains the roads, the water, the mobile networks, and emergency services. It strains the very infrastructure that a darkened grid is straining too. The same evening the engineers watch their frequency screens. The roads fill up. And I must say the safety part very plainly, because it is simple. For the whole eclipse, you must protect your eyes with certified glasses. Not sunglasses, not a phone screen, and certainly not smoked glass. Only certified eclipse filters that meet the international safety standard will do. The sun can burn a permanent blind spot into the back of your eye, and you will not feel it happening, because the retina has no pain. There is exactly one single exception, and it is heartbreakingly brief. During totality itself, and only then, you may finally look completely unaided. The instant the first bead of sunlight returns, the glasses go straight back on. In Spain, with the sun so low, that window is achingly short. It is 1 minute and 45 seconds in Oviedo, at the very most. It is only 29 seconds on the northern edge, over in Bilbao. Blink, and you can miss the one naked eye view of a star. Millions of people, having travelled thousands of kilometres, get 2 minutes. And they gamble it all on a single clear patch of horizon. But those inside the ribbon are, in the end, the lucky ones. Because most of Europe will get something that only looks close. Part 19. The map of who sees almost everything. Let me show you the far wider map of this whole eclipse now. The ribbon of totality is narrow, but the shadow itself is broad. Around that dark core lies a much larger, softer, fuzzy shadow. Astronomers of the sky call that outer shadow the penumbra. Inside the penumbra, the sun is only ever partly covered by the moon, and the penumbra falls across a truly vast stretch of the world. Most of Europe will see a genuinely deep partial eclipse that day. Parts of North America and Northwest Africa will see it as well. London will see the sun, about 91% covered over. Dublin will see roughly 94% of it hidden away. And here is the cruel twist that waits near the ribbon's very edge. Madrid and Barcelona both sit just outside totality's narrow path. They will see the sun 98 or 99% covered. That sounds almost identical to totality, but it truly is not. Remember Duncan's sharp warning about the whole 90% idea? 99% covered is still, fundamentally, bright ordinary daylight. That last 1% of the sun is still blindingly, savagely bright. It is more than enough to keep the sky blue and the corona hidden. The stars do not come out overhead at 99% covered. The temperature barely drops, and the birds stay perfectly calm. You cannot safely remove your glasses for even a single second there. The difference between 99 and 100 is not a small one. It is the difference between reading about the sea and actually drowning. It is the whole reason people drive so far to the centerline itself. They will pass right through Madrid, where the eclipse is nearly total, and they will keep on driving north into the true, real ribbon. Because the ribbon is where day genuinely becomes night for 2 minutes. So picture the whole map on that single August evening across Europe. A thin band of true darkness cuts across northern Spain itself, and around it, a vast zone of eerie, incomplete, uneasy dimming. Hundreds of millions of people will look up across the continent. They will see a bite taken cleanly out of the low sun. Most of them will believe they have seen the whole eclipse, and in a limited sense, they will have seen a version of it. But only those in the ribbon actually see the corona itself. Only they stand inside the moving shadow of the moon overhead. Hold that distinction, because the grid simply does not share it. The grid does not care about the visual ribbon at all. The grid across the whole partial zone loses its solar power. Even a 99% partial hides 99% of the sun. So solar farms across all of Spain feel the deep bite together. Farms across France and beyond feel a shallower version of it. The visual spectacle belongs only to that narrow ribbon of totality, but the electrical event belongs to fully half of a continent. That is why Enzo E thinks in terms of the whole shadowed zone. It does not track the corona at all, only the total loss of power. The moon casts one single shadow that means two different things. To the crowds, it is a spectacle only inside the ribbon. To the grid, it is a challenge across the entire penumbra, and to plan for that challenge, you need one thing above all others. You need to know exactly when that shadow will arrive. Which brings us to the ancient clockwork that makes it possible. Part 20. The clockwork that lets us know the second. Here is something that should sound impossible, and yet it is routine. We know the eclipse's timing to the second, decades in advance. We know its path across the surface of the Earth to the meter. There is a table, computed long ago, for every city in its path. It tells you exactly when totality begins in Burgos, or in Len. So how do we know the sky's future with such extraordinary precision? The answer is one of the very oldest sciences that humans have. For thousands of years, people watched the sun and the moon closely. They tracked the rhythm of eclipses across many long generations, and eventually they found that eclipses repeat in a long, steady cycle. That cycle has a name handed down from deep antiquity, the Saros. After about 18 years and 11 days, the whole pattern nearly repeats. The sun, moon and earth return to almost the very same alignment. So one eclipse is followed by a similar one, exactly one Saros later. String all those repetitions together and you get a whole family. Astronomers call each such family a Saros series, numbered and carefully tracked. The eclipse of August 12th belongs to one such long series. Each eclipse in the family shifts a little across the face of the globe, and by understanding the cycle, we can project it far into the future. Fred Espenak spent an entire career computing exactly these predictions. He worked with NASA and became widely known for his eclipse tables. His calculations tell chasers precisely where to stand and when. The precision here is not luck at all, but pure celestial mechanics. The motions of the moon and earth follow known physical laws. Those laws do not crash, and they simply do not drift over time. Feed them into the mathematics, and the distant future appears clearly. That is exactly why the operators can plan so well for August 12th. Remember, I earlier called predictability their single greatest weapon of all. Here is precisely where that weapon actually comes from in the end. You cannot ever prepare for a fault that you cannot foresee coming. The April blackout, remember, gave the operators no warning at all. But this eclipse has been marked on the calendar for many centuries. Every battery, every import, and every plan rests entirely on that. The same mathematics that thrills the chasers quietly arms the engineers. One group uses the prediction to go choose a clear hillside. The other uses it to schedule the grid's careful defences. The moon sends a kind of calendar invitation, precise to the second, and both audiences, in their own different ways, reply to it. Keep that phrase in your head, a calendar invitation, sent centuries early, because it marks the exact line between two very different kinds of danger. The moon warns us centuries ahead of time before its gentle theft, but something else can take the sun's power with no warning at all. And before we reach that something, we should follow the money instead, because holding the grid steady through an eclipse is never actually free. Part 21. What it costs to hold the sky steady. There is a whole dimension to this that I have not touched yet. Balancing a grid through an eclipse is not free at all. It has a price, and that price quietly finds every one of us. It shows up in a place most people never connect to the moon. It shows up right there in the electricity market itself. Here is something most people simply do not know about their power. Electricity is bought and sold continuously, much like a live auction. Its price changes not by the day, but by the hour. Sometimes it changes by the minute, driven by supply and demand. It follows the same ruthless law I laid out at the very start. When the sun blazes at midday, cheap solar floods the whole grid. There is so much supply that the price of power can crash. In solar-heavy grids like Spain's, it can even go negative. Producers briefly pay other people just to take power nobody needs. Hold that strange fact for a moment, power worth less than nothing. Then, in the evening, the sun fades and demand spikes hard upward. Everyone comes home at once, and the price of power soars. The grid scrambles for every last megawatt that it can possibly find. It reaches for the fast, flexible, and most expensive plants around. Now drop a total eclipse straight into that live market. In a couple of minutes, you switch off the very cheapest power. Solar costs almost nothing to run once it is finally built, and to replace it, the grid reaches for its priciest options instead. It reaches for gas peakers, for imports, and for discharging batteries. So the eclipse does not just stress the grid physically that day, it stresses the grid economically at the very same moment too. For those minutes, the cost of keeping power steady jumps sharply. You pay premium prices for premium flexibility, exactly when you need it. In the 2024 American eclipse, operators watched prices swing hard. The ramp hit the market, and the prices moved right along with it. It is, in miniature, a winter cold snap or a summer heat wave. It is a moment when the grid pays whatever it truly takes. And this is exactly where the batteries change the economics as well. A battery charged at midday, when solar was nearly free, quietly waits. Then it discharges during the eclipse, when replacement power is expensive. It is not just stabilizing the grid in that tense moment. It is buying low and selling high across the whole day. It is, in effect, arbitraging the moon itself for a profit. That is not a flaw in the system in any way at all. That is the entire business model driving the whole battery boom. It is precisely why 29 gigawatts appeared in a single year. The eclipse is exactly the kind of event that batteries feed upon. Every ramp, every price spike, every sudden loss is an opportunity. The moon pulling the sun away is, to a battery, simply payday. Keep that image in mind, because it flips the whole fear around. The very thing that threatens a fragile grid also rewards the batteries, and the batteries, in turn, are what make the grid less fragile. So when I say the grid will probably hold, understand something important. Holding the grid is not passive at all, but an enormous coordinated act. It is paid for in real money, and executed in real time. It is done by markets, and machines, and people in the room. They work so 2 minutes of darkness in the sky mean nothing. They mean exactly 0 minutes of darkness down on the ground. The price of that is completely real, folded into the cost of power. And that invisibility is not unique to Spain at all, either. It reaches out across every single border the grid touches, because Spain does not actually face this eclipse all alone. Part 22. The borrowed power across the border. Let me widen the picture from one country out to a whole continent. Spain is not an electrical island floating quietly all on its own. It is wired directly into the vast grid of continental Europe. Giant cables, called the interconnectors, tie all the countries closely together. Spain connects onward to France, straight through the Pyrenees Mountains. France then connects onward to Germany, to Italy, to the whole. Together they all form one single, enormous, synchronous machine that spans borders. Across that whole machine, the frequency beats as one shared pulse. When it is 50 Hz in Madrid, it is 50 in Berlin too. The whole continent's vast choir sings together in a single key. And that deep connection is a genuine source of enormous strength. If one country runs short, its neighbours can quickly feed it. Power flows across the borders in an instant, following the demand. So when the eclipse dims the Spanish solar, France can help out. It can send power flowing south across the Pyrenees Mountains. The moon's shadow does not fall on all of Europe equally at once. As it darkens Spain, other regions still have their full sun. Their surplus power can then flow toward the sudden shortage. That sharing of power is one of Europe's great engineering achievements. It is exactly what held the grid together back in 2015. But shared strength always carries a shared risk along with it. Remember the April blackout that struck the whole Iberian Peninsula last year? When it collapsed, the cables to France tripped and disconnected fast. The very links meant to help suddenly became a liability instead. The peninsula was cut loose, and it fell entirely on its own. So the interconnectors are, in truth, a genuinely double-edged tool. In normal stress, they spread the load and steady everyone together. In a fast, violent fault, they can trip and isolate a region. A grid tied to its neighbours borrows their stability every day. But it also shares directly in their sudden troubles too, and here is the subtler point about the eclipse specifically. The full shadow crosses Spain, but the partial shadow crosses France. France also has its own large and growing fleet of solar, so France loses some of its own solar at the very same time. The help it can send is smaller than on a normal day. The whole neighbourhood dims together at the same time, though unevenly. That is exactly why ENTSO-E coordinates across all the borders. No single country plans for this coming eclipse entirely on its own. They plan together as one connected system, sharing all their forecasts. They pre-arrange well in advance who will lean on whom. The control rooms across the whole continent stay in close contact. That coordination is exactly what Statius praised back in 2015. He called it a clear success of European regional cooperation, and that same cooperation now faces a considerably harder test. Because the solar fleet is far larger and the grid is far lighter, the borrowed power still flows across the mountains, as before, but every lender is now dimming a little bit all at once. Hold that in your mind: shared light and also shared shadow. The strength and the risk both travel down the very same cables, and beyond those cables lies a deeper vulnerability still to come. Because the sun does not only leave when the moon blocks it. Sometimes the sun reaches out and strikes the grid directly. Part 23. Where the corona goes when it leaves the sun. Return with me to that crown of fire the people will photograph. The corona is not a still, decorative halo around the sun. It is a furnace, constantly boiling material outward into empty space. From it streams the solar wind in every single direction. That wind is a river of charged particles leaving the sun forever. It blows outward at hundreds of kilometers every single second. It sweeps past all the planets, including our own small Earth. Most days, our planet's magnetic field simply shrugs it off. Our world sits inside a large protective magnetic bubble around it. That bubble deflects the ordinary solar wind harmlessly around us. But the sun does not always blow steadily and calmly like that. Sometimes the corona erupts in a sudden violent outburst instead. It hurls a colossal cloud of particles and magnetic field outward. Scientists call that event a coronal mass ejection of material. It can carry billions of tons of matter along with it. It can race across space at millions of kilometers per hour. And if one is aimed directly at Earth, it strikes us hard. It slams into our magnetic field a day or two later on. It sets that whole magnetic field ringing and violently shaking. And a shaking magnetic field does something down at the ground. It induces stray electrical currents in any long conductor there. It induces them in pipelines and in long railway lines everywhere. Above all, it induces them in the vast web of a power grid. Those are currents the grid was simply never built to carry. Keep that firmly in mind, because we have seen the result before. This is the very danger that the eclipse only quietly hints at. The same corona that dazzles the crowds can, another day, attack. And this attack comes with no moon involved in it at all. When scientists study the inner corona during totality, this is exactly why. They are studying the true birthplace of that larger threat. They want to know how the sun launches these enormous storms. They want to forecast them well before they ever arrive here, because a warning of even a single day is genuinely precious. It gives the grid operators time to prepare their defences. They can take their vulnerable equipment safely offline well in advance. They can do just what Italy did with its solar in 2015. They can take the hit on their own terms and their own schedule. But to warn us, they must first understand the corona itself, and the corona guards its innermost secrets very closely indeed. Our satellites cannot see that crucial inner layer cleanly at all. Only the moon, during a total eclipse, reveals it fully to us. So the 2 minutes of totality serve a hidden practical purpose. They are a rare look at the mechanism of a loaded weapon. The crowd sees a beautiful crown, while the scientist sees a lit fuse. And the modern world is more exposed to that fuse than ever. Think of everything that now hangs entirely on the power grid. Think of the satellites overhead that guide all of our planes. Think of the GPS that steers our ships and our phones. All of it is deeply vulnerable to a genuinely violent sun. The very technologies that run our lives are the exact targets, and they are targets that an eclipse itself cannot ever damage. An eclipse is gentle, brief, and perfectly scheduled centuries ahead. A solar storm is violent, prolonged, and only barely announced. Hold that sharp contrast, because it defines everything still ahead. The moon is rehearsing, on a timetable, what the sun could do. And the last time the sun did it for real, it left a mark. Part 24. The danger the eclipse is only rehearsing. Everything so far assumed the moon is the one taking the sun away. It takes it politely, on a schedule, and hands it right back. It is predictable, brief, and perfectly timed down to the second. But the sun has another way to reach a distant power grid, and it is neither polite nor predictable in any way at all. Let me take you back to the 1st of September, 1859. an astronomer named Richard Carrington watched a brilliant solar flare erupt. It became the largest geomagnetic storm in all of recorded history. Within a day, the storm slammed into the Earth's magnetic field, and the Earth of 1859 had almost no electrical technology. There were no power grids, no satellites, and no computers anywhere. Yet even then, the great storm still left its unmistakable mark. It set telegraph systems sparking right across Europe and North America. Operators received real electric shocks from their own equipment that day. Some telegraph lines actually caught fire inside their own offices. And here is the truly eerie part of the whole story. Some lines kept working even with their batteries fully disconnected. They ran on nothing but the current the sun had induced. Auroras glowed so brightly that people rose, thinking dawn had come. That all happened in a world lit by gas lamps and candles. Now imagine that very same storm landing on the world we built. Hold that thought, because we got a much smaller taste of it. Go forward to the 13th of March, 1989. A geomagnetic storm, far weaker than Carrington, reached into Canada. It struck the power grid of the province of Quebec directly, and in about 90 seconds, the entire grid completely collapsed. 90 seconds, from a healthy grid to a whole province gone dark. 6 million people lost their power in the dead of a winter. They lost it for around 9 hours in the brutal Canadian cold. The induced currents even damaged a transformer far to the south. They damaged it as far away as the state of New Jersey. And the storm that did all of that was not even a great one. A true Carrington-class storm today would be far, far worse. It is one of the genuinely serious risks that keep experts awake. It is a low probability but high consequence threat to modern life. Now here is the crucial distinction, so let me be very precise. The eclipse and the solar storm are exact opposites in one way. The eclipse is perfectly predictable and known many centuries ahead. That predictability is the whole reason the grid can prepare for it. It is the reason I keep telling you the lights will hold. But a solar storm gives us a single day of warning, at best. And sometimes it gives us far, far less than even that. You cannot pre-position for a Carrington event as you can an eclipse. You do not get centuries of quiet notice, but only a few mere hours. So hold August 12th in its very largest possible frame now. It is a scheduled, survivable and genuinely beautiful dress rehearsal. It rehearses a threat that is neither scheduled nor guaranteed survivable. The moon does gently what the sun could one day do with violence. The moon does it to one country, for only 2 short minutes. The sun could do it to the whole daylit half of Earth. And the corona revealed for those 2 minutes is that threat's face. The engineers who quietly see a stress test are not being paranoid. They are being professional, and they truly know the difference. The difference is only which body reaches out for the grid, and only one of those 2 bodies sends a calendar invitation. Let me say that again, because it is honestly the whole thing. Only one of them sends a calendar invitation, centuries in advance. That single fact separates a spectacle from an outright catastrophe. So the crowds will admire exactly what the engineers quietly fear. But the shadow has fallen on our world many times before, and each time it fell, it left us something we did not have. Part 25. What the shadow taught us in 1905. Eclipses have a strange way of marking our turning points in understanding. This is far from the first time the shadow has crossed Spain. Go back with me to the 30th of August, 1905. That was the last totality over mainland Spain before the one now coming. It was fully 121 years ago in the past. And it did not fall on solar farms and control rooms at all. It fell on a country of horses and simple telegraph wires. But it drew serious scientists from all over the entire world. Expeditions came from France, from Britain, and from Italy that year. The United States Naval Observatory sent its own people as well. They hauled heavy brass telescopes and fragile glass photographic plates. They carried them to towns like Burgos and distant Daroca. Some of them even went up in floating hot air balloons. They rose to get above the thick haze near the ground. All of it was to spend a few minutes studying the corona. Totality that particular day lasted 3 minutes and 46 seconds. Hold that duration up against what Spain actually gets this time. Now the mainland gets well under 2 minutes at its very best. In 1905, they got nearly twice as long as that, and they came because an eclipse was then their only laboratory. In that era, it was one of the only ways to study the corona. There were no coronagraphs and no space telescopes anywhere yet. The darkness itself was a laboratory that opened for a few minutes. Then it closed again for years, until the very next one came. So they chased it exactly as the chasers still chase it today. They set up their delicate instruments and waited for the shadow, and when it finally came, they captured everything they could. They photographed the corona on their fragile, light-sensitive glass plates. They measured its faint shape and its delicate outer structure. Each eclipse added just a little more to the growing record, and piece by piece, the sun's atmosphere slowly gave up its secrets. Think of the sheer courage in that whole scientific undertaking. They travelled for weeks, by ship and by rattling rail, to arrive. They carried delicate glass instruments right across a whole continent. They gambled everything on a single clear Spanish sky that afternoon. A single passing cloud could ruin years of careful preparation. It is exactly the same gamble the chasers face this coming August. The horizon, the weather, and the fragile chance of true clarity. Very little has actually changed in that timeless human bargain. What has changed completely is the country lying beneath the shadow. In 1905, the eclipse threatened absolutely no one's power. There was no grid to lose, and no solar to darken then. The shadow was purely a thing to study and to admire. Now it is also, unavoidably, a thing we have to survive. That is the enormous difference the passing century has made. The same shadow on the same soil means far more now. It is science, and spectacle, and a stress test all at once. But the single greatest thing an eclipse ever taught us came later. It came just 14 years after that Spanish morning in 1905, and it did not merely add another line to the record. It completely rewrote our whole understanding of physical reality itself. Part 26. The eclipse that proved Einstein right. Let me take you now to the 29th of May, 1919. On that single day, an eclipse did something truly extraordinary. It tested an idea that most scientists at the time did not believe. A young physicist named Albert Einstein had made a bold prediction. He said that gravity itself could actually bend a ray of light. He said the sun's mass would warp the very space around it, and so starlight passing near the sun would be visibly deflected. Its apparent position in the sky would shift by a tiny amount. It was a strange and genuinely radical claim about all of reality. The only way to test it in practice required an eclipse. You had to photograph the stars sitting right beside the sun, and you can only ever see those stars during a total eclipse. At every other time, the sun's fierce glare completely hides them. So British expeditions set out that year to catch the shadow. One went to the island of Principe, off the coast of Africa. Another went to Sobral, in Brazil, far across the wide ocean. Arthur Eddington himself led the expedition to distant Principe. They waited, as all eclipse chasers wait, for the sky to clear. And when totality finally came, they took their careful photographs. They captured the faint stars sitting near the darkened sun. Then they precisely measured the positions of all those stars. And the starlight had shifted, just exactly as Einstein had foretold. It had shifted by very nearly the amount that he predicted. The results were announced that November to the whole waiting world, and overnight, Einstein became the single most famous scientist alive. General relativity had been confirmed in the shadow of an eclipse. Think for a moment about the sheer weight of that quiet moment. Our entire modern understanding of gravity was put to the test there. The physics of space and time was checked against the real sky, and the physics that makes your phone's GPS work was born there. The darkness people once feared as an evil omen now served science. It became the one condition needed to catch the universe bending. Hold that, because it reframes exactly what the crowds will watch. The corona hanging over Len is the very same corona from 1919. It hides the same faint stars that Eddington once photographed. It is a laboratory that still opens for us, for a few minutes. Now come forward with me to the 11th of August, 1999. That was the last total eclipse to cross mainland Europe before now. It was the very last one before the eclipse we are awaiting. Its dark path ran from Cornwall across France and across Germany. It crossed Austria, Hungary, Romania, and on toward Turkey and India. More than 300 million Europeans stood inside its wide zone. They were inside either the partial or the total shadow that day. The European Space Agency itself described what happened next across Europe. More than 300 million people became eclipse watchers and chasers. For a single day, an entire continent turned into amateur astronomers. It was one of the largest shared experiences of the sky ever. And then the shadow moved on, exactly as it always does. Europe did not see another mainland totality for 27 long years. Not until this very eclipse, now just 11 days away from us. So place August 12th firmly in that long unbroken line. It descends directly from 1905 and from 1919. It descends from that continent-wide day back in 1999. The same shadow that once brought scientists to Burgos now returns. The same darkness that confirmed relativity is coming back again. But one thing has never once been true before in this line. This time, the country beneath depends on the sun for its power. So the eclipse is no longer only a thing we simply watch. It is now a thing we must, for 2 minutes, do without. But before we ask what happens on the day, one more strangeness. Part 27. Why the corona burns hotter than the fire below. I told you earlier that the corona defies all ordinary sense. Its sheer temperature simply should not be possible at all. Let me now return to that deep problem in full. The visible surface of the sun is hot beyond easy imagining. It sits at around 5,500 degrees Celsius. That surface is where all our light and warmth come from. It is called the photosphere, which means the sphere of light, and high above that surface floats the thin and faint corona. The corona is not somehow cooler than the surface beneath it. It is, quite impossibly, vastly and dramatically hotter than that surface. It reaches somewhere between 1 million and 3 million degrees. Sit with the pure strangeness of that single fact for a moment. The atmosphere is hundreds of times hotter than the surface below it. Everywhere else in nature, heat fades as you move away from it. Move away from a fire and you steadily grow cooler. Move away from the sun's surface and you somehow grow hotter. It is as if the air above a candle were hotter than its flame. Physicists have wrestled hard with this puzzle for many generations now. They call it, plainly, the coronal heating problem of the sun. And it remains genuinely unsolved, even in this modern day. Something is pumping enormous energy up into that thin outer layer. Something heats it far beyond the temperature of the surface below. But exactly what that mysterious something is remains genuinely uncertain today. There are two leading suspects at the heart of the mystery. The first suspect goes by the strange name of nanoflares. These are tiny magnetic explosions scattered all over the sun. They are small individually, but they are utterly countless in number. Together they could pour immense heat up into the corona. They flicker across the sun's whole surface constantly and mostly unseen. The second suspect is a family of magnetic waves instead. The sun's magnetic field can carry energy upward from below. Waves ripple along it like waves running down a rope. They travel up and then break apart in the corona above, and in breaking, they could deposit all of their carried heat. Both ideas are plausible, and both are at least partly supported, but neither one has yet fully and finally closed the case. To help settle it, we actually sent a probe to the sun. The Parker Solar Probe flew closer to it than anything before. It dove directly through the outer corona of the sun itself. It flew straight through the very layer that is in question. It measured the fields and the particles there directly, up close, and it has sent back genuinely stunning new data ever since. It has sharpened our whole picture of the corona's strange behaviour, but even it has not yet fully ended the long debate. The coronal heating problem is, remarkably, still wide open today. So when the crowds look up on August 12th, remember this: they are looking directly at an unsolved problem in physics itself. It hangs there in the sky, silver and structured and silent. It is not merely a beautiful crown to be photographed. It is a genuine question our whole species has not yet answered. And answering that question is far from merely academic. Remember, the inner corona is the launch pad of the solar wind. It is exactly where all of our space weather is truly born. Understand the heating, and you begin to understand the storms. Understand the storms, and you can finally begin to forecast them. Forecast them, and you can actually protect the vulnerable grid. So the mystery in the corona is, in the end, a practical one. The unsolved physics up there quietly guards a very real threat, and the eclipse gives us a rare, clean look right at it. But to truly appreciate those 2 minutes, you must understand their shape. Because totality is not one single event, but a sequence of 4. Part 28. The 4 moments that make totality. Let me slow all the way down and take the eclipse apart carefully. It is not really one event, but a sequence of 4 distinct ones. Astronomers formally mark those 4 separate moments as the 4 contacts. Each one is its own separate, distinct moment in the sky above. Understanding them is honestly how you truly learn to watch an eclipse. The first contact is by far the gentlest of them all. It is the exact instant the moon first touches the sun's edge. A tiny dark bite simply appears at the edge of the disk. To the naked eye alone, nothing at all seems to change. The daylight around you is still completely full and strong. Only through your eclipse glasses can you even see that first bite. From there, the moon creeps slowly across the bright disk. Over the next hour or more, it steadily eats inward. The bite grows into a thinning crescent of remaining sun, and still, remarkably, the world stays surprisingly bright around you. Human eyes quietly adjust, hiding the slow dimming from your notice. This is the long, patient, deceptively calm first act of it. Then comes the sudden acceleration toward the second contact itself. In the final minutes, the crescent thins down to a bare sliver. Now the light finally begins to feel genuinely wrong to you. The strange silver quality I described creeps into the air. The temperature around you begins its sharp and very noticeable fall. And then, that last sliver breaks into the Bailey's beads. Those beads are sunlight shining through valleys on the moon's edge. They shine where the lunar mountains happen to let light pass. One by one, the beads wink out in a quick sequence, until only a single brilliant bead remains, blazing there all alone. That very last remaining bead becomes the famous diamond ring. It blazes on a faint circle of newly visible coronal light. And then the diamond ring itself finally goes fully dark. That instant is the second contact, the true start of totality. Now, and only now, the full corona appears in the sky. Now, and only now, you may safely lower your glasses. The black sun hangs there, ringed all around in silver fire. This is the beating heart of the whole experience itself. In Spain, this heart lasts for well under 2 minutes. In Oviedo, it lasts 1 minute and 48 seconds. On the northern edge, at Bilbao, it lasts far less time. It is a mere 29 seconds there at that edge. Every single second of it is precious and fleeting and gone. And then it ends just as suddenly as it first began. The third contact is the abrupt, painful end of totality. On the far side of the moon, the sunlight returns at last. A diamond ring flares again on the exact opposite edge. The glasses must go straight back on your eyes at once. Bailey's beads reappear, and then a slowly growing crescent follows. The corona vanishes back into the returning glare of day, and the strange world around you now begins to reverse itself. The light climbs back, the warmth returns, and the birds stir. The long fourth act now plays itself out fully in reverse. The moon slowly uncovers the whole sun over the next hour, until the fourth contact, when the moon finally departs entirely. The last dark bite closes, and the sun is whole again. And in Spain, something genuinely poignant happens right at this point. Because totality comes so near sunset, watch the timing closely. For many cities, the sun actually sets during the partial phase. The eclipse is not even finished when the sun goes down. The still-bitten sun slips quietly below the western horizon. So the shadow and the ordinary sunset arrive very nearly together. It is a double dusk, a strange folding of 2 separate nights. Keep that rare image in mind as we return to Earth. Because a whole country is about to do what few ever do. It is about to stop, all at once, and simply look up. Part 29. What a country does when the sun goes out. We have seen exactly what an eclipse does to a fragile grid. Now consider what a total eclipse does to an entire country. Because a totality is a genuinely rare kind of shared event. It stops millions of people at the very same single instant, and our own recent history shows us just what that looks like. Go back to the 21st of August, 2017. A total eclipse crossed the entire width of the United States. It ran from Oregon in the west to South Carolina in the east. It was widely called the Great American Eclipse of that year, and it became a genuine national event unlike almost any other. An estimated many millions of people travelled to see the totality. Small towns all along the shadow's path swelled enormously overnight. Highways clogged solid for hundreds of miles in every direction. Hotels sold out completely more than a full year in advance. It was one of the most watched sky events in all history. Then it all happened again on the 8th of April, 2024. Another total eclipse swept right across North America once more. It crossed Mexico, the United States, and finally Canada that day. And once again, a whole continent stopped simply to look up. These two events teach us a great deal about what to expect. First, the human tide is genuinely enormous and highly concentrated. People funnel themselves into one narrow ribbon of land together. They pack out all the small towns sitting on the centre line. Second, the demand on the grid shifts in a strange way. As people stop their work to watch, some electricity load drops, offices pause their machines, and factories idle for a little while. But other demand rises as people travel and gather in crowds. The net effect is a complicated, shifting, hard-to-predict load, and it lands at exactly the moment the solar power dips away. So the grid faces a moving target on both sides at once. Supply falls with the sun, and demand jumps around unpredictably. That is part of what makes the careful planning so difficult. Third, the emotional effect on ordinary people is genuinely real. Crowds fall completely silent, then erupt as totality finally hits. Strangers embrace each other, and many are moved to open tears. It becomes a shared human memory for an entire region at once, and Spain is now bracing hard for its own version of this. But Spain's version carries one unique twist along with it. Remember that the eclipse there happens very near to sunset, so the crowds will not simply disperse into a bright afternoon. They will watch the black sun, then the true sunset behind it. Then they will face the long roads home in full darkness. Tens of thousands of cars, all moving at once, at night. They move along winding mountain roads and busy coastal highways. It is a real logistical challenge stacked on an astronomical one. And with those crowds comes a genuine economic force too. When totality crosses accessible and beautiful country, the people always come, and they bring their wallets and their spending right along with them. They fill the hotels, the restaurants, and the campgrounds completely. Small towns can earn a full year of tourism in mere days. The American eclipses prove this economic windfall very vividly indeed, and Spain in peak summer season expects exactly the same tide. Hotels in Oviedo, Burgos and Len filled up many months ago. So a country pausing to look up is a beautiful thing. It is also quietly an enormous coordination problem hiding underneath. The same evening the grid holds its breath, the roads overflow. Both the human strain and the electrical strain peak together. Both fall on the very same darkened region at the same hour. Keep that convergence in mind, because it grows only larger. But how did Spain come to depend so heavily on the sun? Part 30. How Spain became a country that runs on the sun. Let me answer a question I have quietly skipped so far. How exactly did Spain ever get to this remarkable point? How did it come to draw a fifth of its power from sunlight? The story is faster and stranger than you might first think. A decade ago, Spain's solar fleet was genuinely quite modest. The country had sunshine in great abundance, but very few panels. Spain is, after all, one of the sunniest countries in all of Europe. Its southern plains bake under clear skies for months on end. That abundant sunlight was always an obvious resource to tap into, but for years, both policy and cost held the whole thing back. Then the price of solar panels collapsed dramatically across the world. Solar panels grew steadily cheaper, year after year after year. What was once genuinely expensive quickly became remarkably affordable instead, and Spain's endless sunshine suddenly made very hard economic sense. So the build-out finally began, and then it truly accelerated. Investment poured into vast new solar farms across the country. Fields all across Castilla y León slowly filled up with panels. Rooftops in the cities added their own small arrays on top, and the national solar numbers climbed with genuinely startling speed. Remember the central figure I gave you near the beginning? Spain now holds a full 50 gigawatts of solar capacity. That is about 1/3 of its entire generating fleet, and much of it arrived within just the last few years. In a single year, it added 8.7 gigawatts of it. That blistering pace would have seemed impossible only a decade ago. Spain set genuinely ambitious national targets for its clean power. It aimed to slash its carbon emissions quickly and deeply, and solar became the powerful engine driving that whole plan. The sunshine that always fell on Spain now powers the country. This is, in most every way, a genuine and real success. Cheap, clean electricity is a truly remarkable achievement to reach. The panels produce no smoke, and they burn no fuel at all. On a bright day, they power many millions of homes together. And they do it at a very low running cost indeed. But every success quietly reshapes the machine underneath it all. As solar power rose, the older plants were used less and less. Coal plants closed their doors for good right across the country. Gas plants ran fewer and fewer hours with each passing year, and along with them went some of that precious spinning steel. The grid grew cleaner and cheaper and much lighter all at once. Lighter, as we have already seen, also means twitchier and faster. The very success of the transition created the new vulnerability. This is not, however, a flaw that is unique to Spain. It is simply the shape of the energy transition everywhere on Earth. The whole world is now walking down this very same path. Spain has simply walked it faster and harder than most others, and that makes Spain a genuine bellwether for all of us. What happens to its grid this August is being watched closely. Other countries can already see their own future written in it, so when the shadow crosses Spain, remember what it crosses. It crosses a country that bet boldly and fast on the sun, and now it must prove that bold bet can actually hold. But recall that 2 Spanish regions once escaped a disaster, the islands that stayed lit. Return with me one last time to that dark April afternoon. The whole peninsula fell into a deep darkness altogether. Tens of millions of people lost their power in one instant, but 2 places kept their lights burning steadily throughout it. The Balearic Islands stayed fully lit through the entire ordeal, and the distant Canary Islands stayed completely lit as well. And the reason those islands survived reveals something genuinely important. Those islands run entirely on their own separate, independent grids. They are simply not wired into the mainland's connected system. They are, in every electrical sense, true islands unto themselves, and that very separation turned out to be their salvation. Engineers actually have a name for this useful quality: islanding. An islanded grid stands entirely on its own 2 feet. It generates and it balances all of its own power alone. It is not tied at all to the fate of its neighbours, so when the mainland collapsed, those islands simply did not. The cascade of failure could not leap across the open sea. The cascading failure stopped cold right at the water's edge. The islands simply carried on, staying calm and completely undisturbed. Now hold that outcome against the mainland's very different fate. The peninsula was all wired tightly together as a single unit. That connection is usually a genuine and great strength. Remember, neighbours share their power and steady each other every day. But in a fast, violent collapse, it became a fatal weakness. The regions all fell together precisely because they were joined. The very links meant to help instead spread the failure wide. This is the deep paradox at the heart of a connected grid. Connection shares strength beautifully on a perfectly normal, quiet day, but connection can also share collapse on a truly terrible one. And it poses a genuine hard question about our future. Should our grids be more tightly connected, or less so? A tightly linked grid pulls all of its shared resources. It can lean on distant help in a sudden shortage, but it can also fall as one single enormous domino. An islanded grid stands entirely alone in a time of trouble. It cannot borrow any strength at all from far away, but it also cannot be dragged down at all from far away. There is simply no easy answer to that deep trade-off. Engineers must balance connection against isolation very carefully indeed here. They build the links, but they also build protective barriers. They design systems that can deliberately split apart when needed. If a fault begins to spread, whole sections can island themselves. They cut loose on purpose to save whatever they still can. It is a controlled retreat, carefully planned far in advance. The Balearics simply survived by already being true islands themselves. Others must learn how to become islands in a real crisis. And this matters for the coming eclipse in a subtle way. The shadow crosses the whole peninsula, and far beyond it too. The partial eclipse dims the entire connected system altogether. So the solar loss is spread across all of those links. That spreading of the load genuinely helps the grid cope. But it also means the whole system quietly dips together. No islanded corner at all is spared the sun's loss. Unlike the April fault, the eclipse reaches everyone at once. The moon's shadow does not respect the grid's careful borders. It dims both the islands and the mainland completely alike. But holding the grid steady takes more than steady giants. It takes reserves, waiting quietly in the wings, ready to act. Part 32. The seconds that save the grid. Let me show you exactly how a grid buys itself precious time. Because when power is suddenly lost, every single second truly matters. And the grid holds several distinct layers of defense ready. Engineers organize those layers by how fast each one responds. The very first layer is the fastest one of them all. It answers in the very first seconds after a sudden loss. This is exactly where inertia does its most vital work. The spinning steel resists the sudden change in the grid. It gives up a little of its own motion to help, and it holds the frequency steady for one crucial moment. That moment is only a few short seconds long at most, but those first few seconds are absolutely precious to the grid. They are, in effect, the grid's own instant physical reflex. Batteries now join this very fastest layer of defense too. They can inject power onto the grid in under a second. They act almost as fast as that physical inertia itself. Together, the two of them catch the very first shock. The next layer of defense responds a little more slowly. It kicks in over seconds and then into minutes afterward. This is what engineers call the primary reserve of the grid. It is made of plants that can quickly raise their output. They ramp up hard to replace the power that was lost. They stabilize the wandering frequency back near its proper target. Then, an even slower layer takes over from those plants. It works over several minutes, gently restoring the full balance. This is the secondary reserve, the grid's steady, patient hand. It brings the frequency back to exactly 50 Hz again. It replaces the fast reserves so those can rest and recharge. And then a final layer works more slowly still than that. It plans out over many minutes and even into hours. It is the tertiary reserve, playing the long game carefully. It quietly rearranges the whole grid for the new reality. So think of it all as a great cascade of defences. There are instant reflexes, then fast muscle, then patient recovery. Each layer covers the grid while the next one prepares itself. It is, in truth, a relay race run against collapse, and the Eclipse tests this entire relay from start to finish. As the solar power falls away, the layers engage in turn. Inertia and the batteries catch those very first seconds together. The primary reserves ramp hard to hold the frequency line. The secondary reserves then patiently work to restore full balance. And through the recovery, they must reverse every bit of it. This whole machinery is exactly what sits behind the calm. When I say the grid will probably hold, this is precisely why. It is not luck at all, but rather deep, layered defense. It is reflexes and muscle and patience, all closely coordinated. But every single one of those layers has a real limit. Each of them can only supply so much power in the end, and each of them takes a little time to fully act. If a shock is too big or too fast, they all strain. That is exactly the fear that the April blackout awakened. The shock that day was simply too big and too fast. The layers could not catch it all in time to help, and the grid came apart completely in just 5 seconds. The Eclipse, thankfully, is a far gentler shock than that. It is slow and predictable and entirely expected in advance. The layers have every chance to catch it as it comes. But they must still be both ready and genuinely deep enough. And that depth depends on a number we should re-examine now. Because 50 gigawatts is not quite what it first seems. Part 33. What 50 gigawatts really means. Let me return now to a number I gave you near the beginning. Spain holds a full 50 gigawatts of solar capacity today, but that particular number quietly hides an important subtlety inside it, and that subtlety genuinely changes the whole shape of the risk. capacity is simply not the same thing as actual output. 50 gigawatts is the absolute maximum the panels could ever produce. It is what they would make under perfect ideal conditions only. But they very rarely produce anything close to that full maximum. They only ever reach it under a clear sky and a high sun. Most of the time, their actual output runs considerably lower than that. At night, of course, their output is simply zero everywhere. In the evening, near sunset, that output is already fading fast. On a cloudy day, the output drops sharply below the maximum. Engineers measure this whole gap with something called a capacity factor. It is the fraction of the maximum that the panels actually produce. For solar power, that fraction is quite modest when averaged out. Across a whole year, it is often a fairly low number. That is simply because the sun is not always shining down. So 50 gigawatts of capacity is, in practice, a bit misleading. The grid almost never actually sees a full 50 gigawatts of solar. It only sees whatever the current sky happens to allow it. And that fact is genuinely crucial for the eclipse this August. Remember that the eclipse over Spain happens very near to sunset. At that late hour, the solar output is already running low, the sun sits low, and its power is already fading toward evening. So the full 50 gigawatts is simply not all at risk. Only the evening's actual output can possibly be lost to the moon, and that evening output is only a fraction of the true maximum. This is the mathematical heart of the whole comfort I offered you. The near-sunset timing genuinely shrinks the real physical loss of power. It shrinks it not because the capacity shrinks, but because output does. The sun was already halfway out the door for the day. The moon simply closed that door a little bit early. Hold that clear distinction firmly in your mind for a moment. Capacity is the big headline number, that full 50 gigawatts. Output is the smaller, real number on the actual day itself. And on eclipse evening, that real output is genuinely modest. That is exactly why the experts expect only a limited effect. Now, I must be careful and completely fair with you here. Modest does not, however, mean nothing at all in this case. A sudden loss of even modest solar still matters a great deal, especially so given the sheer speed of the loss and the return. The ramp is still steep, even when starting from a low base. So the comfort here is genuinely real, but it is only partial. The near sunset timing helps the operators a great deal, truly, but it does not erase the underlying challenge for the grid completely. It shrinks the trough of the dip, but not the ramp itself. And the ramp, remember, was always the real danger all along. Keep both of those truths in your hand together at once. The total loss is smaller than the headline number would suggest, but the sheer speed of it still genuinely tests the grid. This is the honest, careful and precise picture of it all. It is not panic, and it is not dismissal, but precision. The number 50 gigawatts is really only a distant ceiling. The real risk lives well below that headline number, near sunset. And the timing pushes that real risk lower still, thankfully. That is the reassurance the actual data genuinely supports here. But there is a reason the deeper caution never fully lifts away, and that reason reaches all the way back into human history. Part 34. The war that an eclipse once stopped. For nearly all of human history, an eclipse meant pure terror. It did not mean wonder or science, but raw and simple fear. Imagine the daytime sky with no explanation at all for it. Imagine the sun itself simply vanishing in the middle of the day. To ancient peoples, it was a genuine catastrophe unfolding overhead. The very source of all life was being visibly devoured. Cultures right across the world shared this exact same deep dread. Many of them believed a great monster was eating the sun. In parts of Asia, people spoke of a sky dragon devouring it. They would shout and bang on drums and metal pots loudly. They were trying, quite literally, to frighten the great beast away, and when the sun finally returned, the ritual seemed to have worked. The banging and shouting had saved the whole world once again. Other cultures instead read eclipses as dire and frightening omens. They were taken as clear warnings of a coming king's death. They were seen as signs of approaching war, or famine, or plague. The sudden darkness was read as the sky's terrible anger. And yet, even inside all that fear, something else slowly grew. People slowly began to watch the sky and to keep records. They carefully tracked exactly when the darkness came each time. The ancient Babylonians kept unusually careful written records of eclipses. Over many centuries, they gathered a very long history of them, and buried within that long history, they eventually found a pattern. They found the very rhythm we now call the Saros cycle. The old terror was slowly becoming a genuine kind of knowledge. Consider one especially famous moment drawn from our deep antiquity. It happened on the 28th of May, 585 before our era. Two great armies were locked in a fierce battle that very day. The Medes and the Lydians had fought a long and bitter war, and right in the middle of the fighting, the sun vanished. A total eclipse fell suddenly across the whole battlefield below. The soldiers took it instantly as a clear sign from the heavens. They laid down their weapons in stunned awe and real fear. The battle simply stopped, and a lasting peace was quickly made. An eclipse had, quite literally, ended a war on that day, and there is a deeper legend attached to this famous event. The philosopher Thales is said to have actually predicted it beforehand. If that is true, it was a truly stunning early scientific feat. It marked a profound shift from omen toward genuine understanding. It was a shift from fearing the sky toward foreseeing it instead. That whole shift took many thousands of years to fully complete. But it is exactly the same shift that we now live within. We no longer fear that the sun is being eaten alive. We book our hotels and carefully pack our telescopes instead. We compute the exact timing of the shadow to the second. We travel toward the darkness now, rather than fleeing away from it. And yet a faint trace of that ancient awe still remains. Watch the modern crowds fall completely silent as totality finally hits. Watch grown adults openly weep at the sight of the black sun. Something genuinely ancient still stirs inside us in that one moment. The old fear became pure wonder, but the deep power remained. Hold that whole long human arc clearly in your mind now. It runs from dragons and drums to physics and precise forecasts. It is the very same event, understood in two opposite ways. And on August 12th, both of those meet in the crowd. But humans are far from the only ones who react below. Part 35. The animals that answer a false night. When totality finally falls, the animals themselves all quietly respond, and their response is one of the quieter wonders of an eclipse. It is the whole living world, briefly fooled by a false night. Consider what that sudden darkness actually does to them all. For a bird, that sudden false dusk feels completely real. The light fades away exactly as if evening has truly come. So the birds simply do what the failing evening light demands. They grow quiet and start heading in early toward their roosts. Their usual morning and evening songs can fall strangely silent. Then, as the light returns, they may begin to sing again. It is a false dawn, arriving only minutes after a false dusk. Bees have been observed returning early to their hives as well. They fly home exactly as if the working day has ended. Then they emerge again once the sun comes fully back. Crickets and cicadas can begin their whole night chorus early. They start up their song in the sudden, unexpected darkness. Frogs too may begin to call out from the water. The whole soundscape of the land shifts and changes around you. It turns from the sounds of day to the sounds of night. And then it shifts back again, all within a couple of minutes. Larger animals also react to the false night in their own ways. Cows and horses have been seen growing visibly restless in fields. Some of them walk slowly back toward their barns and shelters. They follow the rhythm that the fading light quietly suggests to them. The farm animals prepare for a night that is not actually coming. Even spiders have been observed responding to the sudden change. Some of them begin to take down their webs at the false dusk. Then they pause, confused, as the daylight unexpectedly returns to the sky. Scientists have studied all of these strange reactions for many years now. Eclipses offer them a rare and valuable natural experiment to observe. They let researchers test how deeply animal behavior is tied to light, how much of what animals do is bound to the sun itself. The eclipse asks exactly that deep question, right out in the open, and ordinary volunteers have long helped to gather the real answers. During past eclipses, people carefully recorded the local animal behavior. They noted exactly what the birds and the beasts around them did. And together, they built a rich picture of nature's response. It is citizen science at its most charming and most accessible. It is ordinary people simply watching the natural world react, and Spain's coming eclipse offers yet another valuable chance for this. All across the path, the animals will answer that false darkness. In the fields, the forests, and along the coastal cliffs alike. The birds of northern Spain will fall suddenly and strangely quiet. Their evening chorus will start far too early in the day, and countless observers will be there, watching closely for exactly this, because it reveals just how deeply all life reads the sky above. Hold that image right alongside the great human crowds now. Above them, people gasp aloud at the sight of the black sun. All around them, the birds go silent in their deep confusion. The whole living world pauses together in that one strange moment. It is bound together, human and animal, by the very same false night, and some of those humans have travelled across the world for it. Part 36. The people who chase the shadow. There is a strange and deeply devoted tribe among all of us. They call themselves, quite simply, the eclipse chasers of the world. Some of them go by an even stranger name, umbraphiles. That word means, quite literally, lovers of the shadow itself, and they will be all over northern Spain this coming August. Let me try to tell you exactly what drives these people. A total eclipse, they will tell you, is unlike anything else. It is not merely a bigger version of a partial eclipse. It is instead a genuinely and completely different experience altogether. And once you have truly seen one, you finally understand them. Many of them describe it using the plain language of addiction. They see one single totality, and then they must see another. They begin to plan out their whole lives around the shadow. They study the paths of future eclipses for many years ahead. They already know where totality falls in the year 2027. They know where it falls a full decade from now too, and they go, wherever on Earth the shadow happens to lead them. They have stood on ships in the middle of vast oceans. They have flown deep into the Arctic just to catch it. They have climbed remote mountains for a slightly clearer horizon. They have crossed wide deserts and endured almost any weather for it. All of that for 2 brief minutes of darkness at midday. To an outsider, all of this can honestly sound quite extreme. Why on earth travel so very far for such a brief sight? But the chasers themselves answer with total and complete conviction. They say those 2 minutes are genuinely worth every bit of it. They say the sight somehow rewires something deep inside of you. And they insist that no photograph or video ever comes close. And there is genuinely real evidence to support their strong claim. Remember exactly what totality actually does to the people who see it. The sudden night, the corona, the strange glow all around the horizon, the bright stars appearing in the middle of the daytime sky, grown adults openly weeping at the overwhelming sight above them. That is not ordinary tourism in any recognizable way at all. It is something far closer to awe, or perhaps even to worship. and Spain now offers these chasers a genuinely rare and special prize. It offers a total eclipse over a beautiful and accessible country. It comes in peak summer with a uniquely low reddened sun. Many of them have waited years for exactly this one chance. Some of them last saw a European totality back in 1999. They have waited 27 long years for the very next one. Now it arrives, at last, over northern Spain in mid-August, and they will not waste a single second of their chance. They study the cloud maps and the forecasts almost obsessively. They pick their exact viewing spots many long months in advance. They keep backup sites ready too, in case of horizon clouds. They are prepared to drive hundreds of kilometres on the day. They will chase a single clear patch of horizon to the very end. For these chasers, the weather forecast is genuinely everything that matters. A single bank of cloud can undo entire years of their planning, so they watch the coming skies like anxious, hopeful hawks. Millions of ordinary people, all quietly betting on one clear sky. Their great reward or their real heartbreak hangs entirely upon it. But this remarkable eclipse is not actually a one-off for Spain, because the sky has something far rarer still in store for it. Part 37. Not one eclipse, but 3. Here is a single fact that quietly changes the whole story. August 12th is genuinely not a one-off event for Spain. It is only the very first of 3 separate eclipses coming. There will be 3 solar eclipses in roughly 30 months, and that fact completely transforms the meaning of it all. Let me lay out the full sequence clearly for you now. The first is this total eclipse coming to us this August. It crosses the north of the country very near to sunset. Then comes a second one, less than a full year later. On the 2nd of August 2027, another arrives. It is another total eclipse crossing right over Spain again. But this time the shadow sweeps across the sunny south instead. It runs directly over Andalusia in the deep summer heat. And it will be a very different eclipse from this one. The sun will sit high and strong in the sky. Totality will last far longer than it does this August. It will be a longer, higher, and much brighter darkness. Then comes a third eclipse in early 2028. On the 26th of January, an annular eclipse crosses Spain. An annular eclipse is a rather different beast from a total one. The moon is slightly too far from Earth on that day, so it simply cannot quite cover the whole sun completely. It leaves a brilliant unbroken ring of fire around itself. That fiery ring will cross Spain in the depths of that winter. 3 eclipses in 30 months all over one single country. It is honestly a rare run of astonishing celestial fortune. Eduard Massana is an astronomer working over in the city of Barcelona. He works at the Institute of Cosmos Sciences in that city. He has put the whole remarkable situation very simply indeed. Spain gets its first mainland totality in well over a century. But it will genuinely not get just the one this time. It will get 3 of them, in very quick succession. For sky lovers, this is a gift almost beyond belief. It is a run of celestial events unlike any in living memory. It will draw the world's eclipse chasers back again and again, and travellers will flood into Spain 3 separate times over. But for those who run the infrastructure, it means something else. 3 eclipses in 30 months is not really a single test. It is instead a whole testing program, repeated and escalating. That is precisely why the Spanish government prepared so carefully. Spain established a special interministerial commission just for all this. It coordinates the planning across the whole run of events. It handles not just the astronomy, but the crowds and the grid. Across all 3 eclipses, they are planning together as one. Now think hard about what all of this means for the grid. It does not face this difficult challenge only one single time. It faces it in 2026, and then again after that, and then it faces it a third time in 2028. And between the eclipses, Spain keeps right on building more solar. The 50 gigawatts of today will only grow larger still. It will be larger by the time 2027 arrives, and larger still by the time 2028 comes around. So each eclipse tests a grid that is even more solar. The whole syllabus gets genuinely harder with each passing sitting. The country keeps raising its own stakes between the exams. And I honestly find that fact clarifying rather than frightening. A single test can always be passed by simple good luck, but a whole series cannot be passed by luck alone. If the grid rides out all three, it truly proves something. It proves a solar grid can survive losing the sun repeatedly, and it proves it with more solar loaded on each time. That would genuinely reassure the whole of the global energy transition. And if it stumbles on any one of these three eclipses, then it finds that weakness on a fully predictable event, which is honestly the safest possible way to ever find it. Either way, the information gained is genuinely priceless to us. This is a grid volunteering itself to be tested 3 times. It is tested by the sky, in full view of the world. The very first of those 3 tests is only days away. So at last we arrive at the real question itself. When the shadow finally falls that evening, what will actually happen? Part 38. What the data supports and what it cannot promise. I have walked you up a long staircase of real concern. Now I owe you the single most honest forecast I can give. It is not the most dramatic one, and not the softest one. It is simply the most honest one the evidence actually allows. And to give it fairly, I must split the future into 2. There are 2 branches ahead of us, and they differ sharply. Let me show you the far likelier of the 2 branches first. In it, everything I described about the preparation simply works. The operators pre-position all their batteries well in advance. The near-sunset timing genuinely shrinks the real solar loss. The 29 gigawatts of new storage do exactly their job. They soak up the ramp and hold the frequency steady. The wind keeps right on blowing, indifferent to the shadow above. Nuclear and hydro hold the steady floor beneath everything else, and imports flow south across the Pyrenees from France as planned. The eclipse comes, and the solar output dips down as expected. Then it recovers, and the frequency needle barely even twitches. Out in the fields, millions of people gasp at the corona, and they never once know that the grid was even tested, because nothing they could possibly feel actually happened at all. This is the outcome that the data most strongly supports. If you asked me to place a bet, I would bet here. I would bet on this calm branch, and I would bet heavily. Even the Spanish utilities themselves are saying almost exactly this. Endesa called the effect on the system a genuinely limited one. It happens, they note, as the solar is already descending anyway. Red Electrica is the control tower, watching everything around the clock. The power will flow, they promise, whether there is an eclipse or not. And they are, in all honesty, very probably completely right. But hold on to that reassurance for just one more moment. Because the instant I offer it, I must open something larger. A perfectly calm forecast is simply not the whole truth here. Here is the second branch, the one that keeps engineers awake. It is not a prediction of disaster, but an honest acknowledgement. A grid running light on inertia tends to hide its failures. Its very worst moments do not politely announce themselves early. The 28th of April had a completely calm forecast too. That held right up until 33 minutes past 12 that day. Nobody at all expected a whole peninsula to fall by dinner. The disturbance that day was not an eclipse in any way. But it proved a hard and genuinely lasting lesson for everyone. On this grid, in this year, the margins are genuinely thin. The distance from normal to total blackout is measured in seconds. This branch is not a claim that disaster is actually coming. It is simply the honest admission of real, irreducible uncertainty. We are running a large scheduled stress on this grid, and we are running it on a machine recently proven fragile. The true test of any system is never its very best day. It is how it behaves when several troubles happen to arrive together. That word, together, is the one I keep circling back toward. A grid very rarely fails from just one single cause alone. It fails instead from a convergence of several separate things. It fails when a scheduled stress meets an unscheduled hidden fault, when the batteries sit lower than planned because of thick cloud, when an import line happens to be down for its maintenance, when a single plant trips off just a fraction too early. No one of those alone is anything like a catastrophe, but stacked together, on a light grid, at the wrong moment, they could be. The eclipse need not be the whole problem all by itself. It need only arrive at the same time as another one. So what does the data honestly support here? In the end, the data genuinely supports calm, and I truly mean that. But the recent history supports deep humility, and I mean that too. The most honest answer of all holds both of those at once. August 12th will very probably be beautiful and completely uneventful. It is a spectacular evening for the sky, and a forgettable one for the machine, and yet a whole room of engineers will stay tense throughout. They will stay tense through every second of those 2 minutes, because they, more than anyone else alive, know the real gap. It is the gap between very probably and actually certainly. And here is the larger loop that I promised you earlier. Even if the grid holds this August, the deeper question only grows, because this is only the first of 3 separate tests, and beyond the 3 of them lies something far worse still. The moon is only ever rehearsing what the sun could truly do. The moon sends its calendar invitation many centuries in advance. The sun, when it finally erupts, will send us none at all. So the reassurance about August is genuinely real, but it is small. It answers only the very smallest version of our question, and it leaves the largest version of that question wide open. Which brings us, at the very end, right back to the beginning. Part 39. The most dangerous moment is when everyone looks away. Let me bring this whole long story back to where it started. I opened with a single simple image for you to hold. On the evening of August 12th, the sun goes out over Spain. For under 2 minutes, the ordinary day becomes a sudden night. A crown of million-degree fire hangs low above the horizon, and I asked you to carry one single question throughout. Are we watching a spectacle, or the first real test of something? The first test of surviving the loss of our own sun? I told you plainly that I would not answer it cleanly, and I fully intend to keep that particular promise right now, because the only honest answer is that it is genuinely both. It is, without any question at all, a true spectacle, and it is without any question a genuine test as well. The strangest part of all is how few will know both. Almost every single person will experience only one of the two. The millions out in the fields will see the pure spectacle. They will see the diamond ring and the silver corona above. They will see the reddened dark and the strange double dusk. They will watch the Perseids fall hours later, into the night. It will honestly be the experience of their entire lives, and they will be completely right to feel exactly that way. But they will never once know the other event occurred. A few 100 kilometers away, engineers watch a different sky. They watch a wall of screens, holding the numbers steady. They watch the frequency and the voltage and the power flow. 2 audiences, one single event at the very same moment. The group watching the beautiful thing sees no fragility at all. It does not even know that the fragile thing exists. and there is the deep pattern beneath this whole long story. The event that draws the great crowd rarely matters the most. The visible spectacle is, in the end, only the distraction. The real test happens quietly in the dark, down on the ground, and it is watched, in the end, by almost no one. The corona draws every single eye upward toward the sky, and the thing that truly tests us happens far below it. So here is the one thought I will leave you holding. The most dangerous moment is never really the crisis itself. It is the quiet moment right after, when everyone looks away. On August 12th, the corona will fade from the sky, the sun will return, and the great crowds will pack up. They will drive home through the deep Spanish night together, and the whole story, for almost everyone, will simply end. The grid will very probably have held through it all, the lights will still be on across the whole country, and the world will quietly move on again by morning. But the vulnerability itself will not move on with it. The grid will still be lighter than it was before. It will still shed its inertia even as it adds more sun. It will still face the very same sunset ramp every evening. It will still face the next eclipse in only a year. And someday it will face a real storm from the sun, a storm that sends no calendar invitation ahead at all. The eclipse itself does not actually create that deep vulnerability. It only lets us finally see it, for 2 brief minutes. Then it hands us back our ordinary, undramatic sky again. And then the danger goes quiet and invisible once more. And invisible is exactly how that hidden danger quietly grows, until a peninsula goes dark on an otherwise ordinary afternoon. So when you watch the coverage that evening, watch the sky. It will be extraordinary, and you truly should watch it closely. But spare a single thought for the room you cannot see. The beautiful thing and the fragile thing happen together, always, and the fragile one will still matter the very next morning. The moon will reach across the dark and take the sun. It will take it from a continent that has learned to depend on it. Very probably, that continent will turn out to be ready. It has batteries now, and a playbook, and a little time. It has known about this exact date for many centuries already. But whether it was a spectacle or a test was never the question. The real question was whether we would still be watching afterward. The shadow is already on its long way toward us now. It will be here in only a matter of days, and it simply will not wait for us to decide.